Welcome back to OARC 26. A couple of quick announcements before we restart. Don't forget it's a PGP signing session tomorrow lunchtime. Send your keys to pgpsign at DNSOARC.net if you want to participate in that. Don't forget to fill in the survey. And also, we've had 2 lightning talk submissions, but there's still room for more. So submissions at, we've had 3 now, so there's still room for maybe 1 or 2 more. So please go ahead and submit. For the social tonight, you need your pink sticker on your badge. You need to have RSVP'd for that. We're full. If anyone RSVP'd and now is doing something else, then please let us know so we can free up the space for people who can't talk. And with that, I'd just like to thank our sponsors again, ICANN for hosting us, VeriSign, and also Salesforce. And I will now hand you over to the session chair for the next session, Ms. Robert Edmonds.
Hello, we have 4 talks on measurement for this afternoon. The first one is Scoring the Root Server System by Jeff Houston of APNIC.
Stand here for camera. Like a well-old machine, isn't it? Hi, I'm Jeff Houston. I'm with APNIC. And this is actually a talk about the root server system. And this is why. Because there are certain times in the transition of the KSK role where the normal expected answer for part of the operation of a validating resolver will gather an answer that is more than 1280 bytes. And it's expected to get that answer and do something useful with it. It occurs on September the 19th, it occurs on December 20, and it occurs on January 11. Oddly enough, October 11 is not a big date. In terms of size, it's those points where the response is variously 1414 and 1424 octets. So, does it happen normally? This is LRoot, which publish the number of times it responds and the size of the response day by day. And I looked on one day, and there it is, and there was absolutely nothing between approximately 1440 and around 2500. It's very, very hard to get the root server to normally respond in that size range. You can get a big answer, dig.any, or you can ask for a very, very long domain name, as long as you possibly can, and make sure you ask plus, eDNS0, DNSSEC, and so on. But it's really hard to construct an answer that's sort of greater than 1400 and less than 25 until we roll the key. So currently, big answers almost never occur. In LRoot's case, 99.994% of all the responses are less than that magic number. So size isn't really a problem for the roots today, but it's going to be. So that's what I said. This leads to 2 questions though, because at some point it's going to be important. And if it's going to be important, the real question is, how should you handle a large response? Even less than 1500, what should you do? And the next question is, what do the root servers do today? So what's ideal? Wow, V4 doesn't have to accept a packet larger than 576 octets, says RFC 790 mumble, 791 I think. But there's a de facto MTU out there in V4 land, and it basically says we all do 10 megabit coax Ethernet, don't we? Yeah, right. We normally expect in V4 packets of up to and including exactly 1500 octets to survive flight through the internet without molestation. And even if there is, the forward fragmenting behaviour, forward and send on the bits forward, is relatively friendly. So large responses in UDP that require fragmentation have a fair chance, and what they're going to encounter is firewalls, and firewalls have relatively interesting behaviours in 4. They discard the trailing frags, not the leading, and some firewalls actually reassemble the packet and then refrag it. So, if you really want to maximise your chances of success and you're quite pragmatic about it, in UDP, you should go up to 1472 octets of payload, so in other words, 1500 octets of packet, and, go from there. What do I do in the DNS? I have a choice at any point as a DNS server to truncate the answer and to force you into TCP. And one of the options is, look, I will not deliver a packet larger than 1500, don't care what your EDNS0 buffer size said, I'm going to maximise the chances, I'm not going to fragment. If you want a big answer, use TCP. And we'll see some root servers do that, others do not. TCP. So I truncate the answer, go and use TCP. In an unrelated test, and I've got a footnote down there in about 2-point font, we actually tested whether resolvers handle TCP, because there's an awful lot of firewalls out there that believe that DNS over TCP is some kind of security thing that should never, ever, ever happen. So they block it. Either that or the resolver doesn't do it, which I find even weirder. 17% of resolvers out there who cover 6% of users don't do TCP. You hand them the problem in UDP, you truncate the answer, you sit there listening for a TCP follow-up, doesn't happen. So TCP is not a very good answer for 6% of the users. Oops. And if you do TCP, what sort of MSS size should you use? And typically with v4, if you account for the fact that there's a 20 octet IP overhead and TCP is 20, you should offer an MSS of 1460. In other words, you should be prepared to send TCP segments of up to 1460 octets without fragmentation. So if you think about it, we can offer 3 stars there. If I can get a root server to deliver up to 1472 octets without fragmentation, that's pretty cool in v4. Don't truncate me until you get to at least 1472. After that, whatever. In other words, don't truncate at 1500 or lower. And for TCP, a big MSS is better than a small. It's slightly more efficient. Not too religious about that, but that's what you should be basically doing. And that thing about UDP packets, respect the EDNS0 buffer size. If the buffer size is lower than 1472, honour that. But if you do those 3 things, you get 3 stars. The nightmare that is v6. For some reason, Steve Deering and his little bunch of merry hackers decided that they would not do the same as v4. They would completely change the way v6 fragmentation worked. So they pulled out this magic number because they observed that there's an awful lot of tunnelling going on in v6. What they didn't observe is that tunnelling is so complete crap that no one should ever have done it. So, 6 to 4, if you're brave enough or stupid enough to use it, swipes 20 octets off the top. So the maximum MSS if you're using 6 to 4, 1480. Teredo does it in UDP because, it can and it loves failure. 35% failure in Teredo, what can you say? 1472 octets, whereas native IPv6 should work at 1500. Why did the spec say 1280? Because when you add the 2 numbers 1024 and 256, you get to 1280. No other reason. No other reason. Jesus. Next thing, when you encounter a packet that won't fit through the next hop, you can't frag and go forward. You have to send a message back to the source going, that was too big, send something smaller. The corrections go backwards. You can only correct it if you get that message. So, then you fragment at source. Firewalls don't like fragments. So some firewalls drop ICMP. The other problem is that fragments in v6 are not like fragments in v4. They generate a new header. It's called an extension header. Many switches don't like extension headers at all, even if they're fragmentation. So you're between an awful lot of rocks out there that extension headers don't work very well. Fragmentation doesn't work very well. You have no idea about ICMP PTBs, but you want to be cool and sexy and use v6, so you're kind of stuffed. So what should it do? If I get back an ICMP and I'm running v6 or I'm running TCP, what does that message actually say to the originator of the TCP packet? You can't ignore it because the other end isn't going to do anything at all. That ICMP has to come back to you in TCP and it has to act like a NAC, like a negative acknowledgement, to cause you to retransmit with a lower MSS. So if you ignore in TCP ICMP v6, you get a black hole of death. You must hear it, you must react if you're using big MSS. In UDP, there is no memory. You have no idea what to do. So when you get back an ICMP from a UDP packet, what you should theoretically do is put an entry in your cache to say, that destination over there can't accept big packets. The next time I go to that destination, I should use a smaller packet. And I put there in a fine note, the other alternative is to say, the DNS is so wonderful and its application behaviour with eDNS buffer size is so brilliant, I'll just drop it on the floor and just pray the DNS is somehow going to correct for this. So, you know, what MSS size should you use in UDP and v6? I would actually argue for UDP, you get a much lower failure rate if you use a 1500 MTU, despite all those problems. So it's a lot of a trade-off about loss rates and fragmentation, but the extension header drop is so prolific, there's nothing else you can do other than basically don't fragment gratuitously. Send the biggest UDP packet you can and pray that it's going to get through. Only fragment as a last resort. And what about TCP? Not every resolver likes TCP, and there are path MTU issues. What you should do is for TCP, do the exact opposite. Big UDP, small TCP. And that should maximise your way through. So, if I offer a 4K eDNS 0 buffer, should you truncate the answer anyway? Should you offer it or honour it, or should you gratuitously truncate? Root servers do it differently. I've no idea which is better, but there is a variation in behaviour. So I think there are 4 stars there. UDP should survive up to 1452 without fragmentation. Don't truncate unless you really have to. If you're going to truncate me right at the top end. You must do something about ICMP. You really, really must. And for TCP, give me a small MSS, not a big one, to avoid TCP black holing. So, 7 stars. I thought I'd test it. I found a query that generates exactly the right answer. It's not very big, but it's bigger than 1280. A conventional query that returns an NX domain, 1296 in v4, 1316 in v6. And so what I do is I query in v4 in UDP. I respond to truncated answers with TCP, and with TCP I offer 1460 and see if I can do it. Much the same in UDP, query in UDP, respond to truncates with TCP. I'm a bit naughty. I actually offer a high MSS in v6 to see what the other end will do. Hopefully it'll do low. If I really want to test things though, I need dig.ini because that's a big answer. Normally the answer is one size, 2,587 octets, except if you ask EH or K or F, or if you ask F when it's served by one group and not another, except when you ask L in v6 and not v4. So, you know, who said root servers were consistent? Not I. They're not. The v6 UDP test, I start asking it again and again and again, 2-minute intervals. Once in a while, I send an ICMP just to see if it's going to react. If it reacts, I time how long it reacts. I do that for 5 hours for every single letter. TCP ICMP is much, 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 much harder because there's so much helpful bullshit hardware out there that trying to intercept TCP and do your own evil thing is quite challenging. But the way it works is you do a normal TCP right up to the point where the large response is set. You intercept the TCP session that's running, stop it, and send an ICMP and see what happens. So, I tested it. I don't have a lot of machinery, not a lot of time. I did not test every Anycast instance from every server. Too much shit. They can do that. I tested it from Brisbane, Canberra in an academic and research network, and rack servers in Dallas, Frankfurt, and Singapore. Whatever I got, I got. If you do things differently in other places, good on you. There are differences between v4 and v6, and I think it's truly bizarre that although there's a v4 and a v6 server for, I think it's, I was going to say iRoot or froot, not sure, it doesn't really matter. I see the Brisbane one in 4, I see the Oslo one in 6. So anyone who thinks there's a happy eyeball story about V6 in the DNS is, on drugs. There isn't. The stuff just is so shocking. So 3 kinds of stars. Gold star if you do it. Black star if it's no, that's a bad thing. And a blank star if what you're doing is irrelevant to the test. A and J. Never hand back big UDP. They truncate at 1280 in V6. So there's no path MTU issues because in UDP and A and J, they're always doing less than 1280. But when they open up TCP, they offer me a Mungo MSS. So there are path MTU issues. And then the real question is, do they respond to path MTU? A does, J doesn't. Oops, not a good idea. B and G, I couldn't make much of that work. They always truncate 4 low. Don't know why, just maybe easier. Whether it's 4 or 6, they basically truncate low. They avoid fragmentation, but they're using a large TCP MSS again. Oops. Do they respond to ICMP? No. Oops. So quite frankly, there's a lot of black and 1 gold. The TCP MSS is actually high, and that's really good. Nothing else works. C, D, E, I, and L, very similar. I think it's something to do with the underlying platform of CentOS and Debian. But, a lot of this is not the DNS behaviour, but it's the platform. They offer a 1500 octet MTU for both protocols. They basically react to ICMP really well for UDP, and they clamp it down for 10 minutes. So there's a cache there that's 10 minutes long. If I send it something, they'll send me smaller responses for about 10 minutes. For that's DNI, the others don't. TCP, always big, not good for V6. So closer, but not quite there. FRoot, now, FRoot's doing some sort of changes in who's serving it and why, but their V6 story when I tested it was not very good. The V4 is just fine, but they're fragmenting UDP low at 1280 when I tested them. That just invites problems. They're not responding to ICMP v6 in either UDP or TCP, and what looked to be something that I thought was sitting inside Cloudflare offer an MSS of 1220, which is kind of cool, but then they just pass me big segments anyway. So here's what I'm going to do. Nah, I lied. I'm going to do something different. Yeah, right, thanks. So, again, just a problem. M, similar sets, subtly different, but similar sets of problems. Again, they're not responsive to ICMP. And H and K, again, very similar, except H responds to ICMP, TCP, K doesn't. And H offers a really high MSS, K does not. So that's the summary of all of this. In V4, the TCP behaviours are consistent, but we're seeing A, B, D, and G truncating the answer even in 4 in UDP, which seems to me to be unnecessary. The fragmentation behaviour of all the other root letters is actually consistent at 1500. For V6, the story is different. A, B, G, and J truncate at 1280. It's unnecessarily vicious, I would have thought. There is fragmentation going on, and C, E, H, and K are odd. If you send a query that has an answer less than 1500, no fragmentation. Perfect. If you do a dig.any, it starts to fragment at 1280, much, much lower. It's sort of as if it's got 2 MTUs running. And that last column, or the last 2, the ICMPs, I saw C, D, E, I, and L responding to ICMPs and UDP, and I saw absolutely no evidence in H and K, even though they gave me big packets, they didn't respond. In TCP, the story is worse. There is only A, D, and H that respond to ICMP and V6 in TCP. So what can I say? B, G, and J have problems when the response is going over 1280. And them alone in V6 would be unlikely to get back an answer to you under most circumstances. That sort of set of configuration options make life rather crap if you're under any kind of path constraint. The others are a bit better. So the overall table, which is basically where I've got to, look, K is almost there. It doesn't respond to ICMP and UDP, but other than that, it would be about as good as you can get. The rest are in varying levels of capability and, you know, from the relatively dismal to the appropriate. I expected more. I don't know about you, but I seriously expected more from these. And we were obsessing in the root role about the key, and maybe we weren't looking at that large packet, because as far as I can see, what this is telling me is that if we didn't have v4, you wouldn't have the DNS. The v6 story is so singularly broken, it just doesn't work with the DNS. And as long as v4 can run in the DNS, we can keep on believing the DNS will operate, roughly. But as soon as that goes away, we're all in trouble. So that's the summary. You can read it yourself about which letters I think will cause more problems than others. So in this key role, it will stress out, particularly B and G, and some resolvers will run into problems as a result. Why will this work? Because as far as I can see, this diversity actually allows a resolver, as long as it is willing to keep churning through letters, to actually get an answer. If it is latched to one letter, it may have made the wrong choice, and that would be a bad thing. Questions?
Hey, Jeff.
Hey.
Shane Kerr, Oracle. I read your blog post about this with great interest, and we actually reproduced some of that work back when I was at BII. So one thing I was wondering, though, is you talked about TCP having relatively high rates of failure. I think like 6% of end users would be unable to get
17% of resolvers affecting 6% of end users, when they get back a truncated answer, do not send me the query in TCP.
So I was wondering if you did any measurements of that in the v6 space only.
Not yet.
Okay, because my assumption, which is quite possibly false, is that v6 enabled resolvers are living in a slightly more modern world than other ones. So maybe TCP works better.
Sorry, did I do that in my out loud voice? Yes,
Right.
Absolutely. That's a fine theory, Shane.
It's
I agree
a
with
possibility. All right, well, it'd be good to see. And I guess one other thing is that I would like to say that fragmentation really sucks, because they use the same algorithm in v6 as they did in v4, where you don't know how many packets you're going to get until you get the last one, which means that it's really tough for firewalls and other middle boxes, and it's just bad design. So
More than 20% of v6 resolvers can't get a fragmented answer because of extension header blocking, I assume. It's really quite bad. Hi.
Hi, Matt Weinberg, VeriSign. You mentioned testing from 5 different locations.
Yeah.
Did you always get the same results from all 5 locations?
I did, but it's hard. You know, it is hard, because to some extent, this whole Anycast stuff, if you think about it really hard, anyone relying on ICMP v6 working in conjunction with Anycast is on drugs. Because the reverse path to which the big packet goes is not the forward path. And although on the forward path, all those routers see the same instance of the route, on the reverse path, you have no guarantee that the intermediate routers that are aligned to the destination see the same Anycast instance of the server. So you might say to me, if you came from B, and whatever, we honour Anycast, we honour ICMP. And the answer is, well, maybe you did, but my test had enough asymmetry that I was sending the ICMP to the wrong node. And this is this sort of issue. We walked into Anycast without understanding v6. Now that v6 is becoming critical, this whole model of asymmetric paths and Anycast and trying to make ICMP work is a bit like juggling 20 balls. There's about 19 too many to make this work well. It's hard.
Andries Ruiz, he said, Nick, with my not DNS and not resolver head on, we tried to tackle this because we got some pull requests about make this configurable. Do you think there's a single set of settings that could apply as a default?
So for v4, 1500. For v6 UDP, 1500. For v6 TCP 1420.
And should we make this configurable in the DNS server?
No, you should not. You should cement this in place, because the broad pool of lunatics that basically take your servers and mangle them will mangle that all the wrong way.
Okay, so...
Maybe I'm sounding too much like Mark Andrews.
Yeah, so do... So what I'm hearing is that we probably need a BCP document to write this down, how it should look like for the DNS servers.
Right, so what you have to do is remember, you will never reliably receive ICMP and TCP in V6. Keep your MSS low, because you can never reliably course correct. For UDP, you're going to have to rely on other mechanisms, but don't unnecessarily fragment. So keep it up as high as you can. And if they don't get the answer, hopefully they will ask someone else.
Okay, so again, can I see the hands if you are willing to volunteer to write such a document? Okay, thank you, Jeff. So we'll talk, because...
So was the camera rolling? No, I didn't do anything.
I'll volunteer Mark.
Wow.
Because with my DNS server implementer head on, it's really too hard to understand what's really happening and what you should do. Okay, so,
No,
so
it's...
thanks. Thanks for doing that work, because it's really needed, and to have a single set of parameters that you could say, this is okay, this is what you should be using, do not configure this.
I emphasise these are engineering designs, not hard and fast rules, but they are essentially what I would think is sensible guidelines that minimise the risk of drop.
Okay.
So I'm happy to write a BCP whatever about it, yeah.
Hi, Jeff.
Hi.
Dwayne Russell's from VeriSign. So maybe I misunderstand something, but on with TCP MSS, it's my understanding that it's sort of bidirectional. That is, the server tells the client, you can send me packets, TCP packets of this size, and the client says, well, you can send me TCP packets of this other different size, right?
You know, there's a number of schools of thought about the MSS and TCP. One of them is the OSPF school that says, you offer me a number, I offer you a number, we both choose the lower,
Right.
which I have seen implemented, and I've actually seen bits of code in some of the stacks. Others might well run the way you go. Have we tested this? Do we understand? To what extent is it an asymmetric? Because in some ways what you're saying is I can receive, because, you know, what you can receive I don't know. But my understanding was the OSPF style. It just goes to a min.
Yeah, I think it's implemented differently in different operating systems. Some do what you said, and others
Well,
don't. And
some operating systems ignore ICMP, you know, V6 completely too.
Right.
And if you're unlucky enough to be running some of those, again, all bets are off. This is just
Right.
bizarre.
so this is certainly an area of uncertainty, and I guess I don't know. I'm a little skeptical that, you know, judging the server's MSS is really the right.
Let me say again, you gave a high MSS in A, and you gave me big answers, big segments in A. In F, it was somewhat weirder. It started as a big segment, and the line interface card chopped it at 1280 and gave me TCP fragments. There's an awful lot of TCP fragments. In theory, that should never happen. In practice, it does. It's weird.
Yeah.
So if you want to be safe, don't send TCP above 1220 in the DNS. Nothing's that big in the DNS yet. So the smaller segment size shouldn't worry you. As a server, you should lock it down.
We've got 1 minute left for questions.
Thanks, Jeff. Jim Reid. Have you done anything to try and fingerprint the root cause of this kind of strange behaviour with segment sizes and segment size negotiation and fragments being lost? Is this down to the kernel configuration of the servers themselves or the middle boxes between them and you?
Look, the root servers operate in a manner that does not disclose a huge amount of information about the way they're set up. So I really don't understand, other than apocryphal conversations, which I can't quote here, about the platforms and versions they're using.
Yeah,
So no, I have no idea.
There are fingerprinting tools which can identify the stacks that have been used.
Feel free to exercise them. Here's some data to work from.
Thank you.
That's a pleasure.
Hi, Jay.
Hi.
Firstly, I would like to say this test. This is very interesting and educational, and I follow this. I repeat this test in the my test bed in the Yeti test bed, and we found some. I want to add something and check with you. You mentioned that the TCP segment is need to less than we expected, right?
For V6,
12.
it needs to be 1220.
1220, yeah. And you mentioned that because the black hole problem, right? The segment may be dropped in the middle. And
If you send a large packet and it's path constrained, you cannot rely that the IPv6 ICMP packet too big message gets back
I
to you.
understood. And according to our experience, we also identify that there is another problem related to the TCP segment, is that if the bigger segment may be fragmented in the middle. So it can also cause...
V6, you don't fragment in the middle.
No, the middle, yeah, if from the host. And
It's fragmented on the line card of the host.
And yeah. So that...
Intel's so helpful. Christ, not.
And another point is true, but I want to point is about the TCP MSS. You put I think you put default TCP MS in the table, right? From the observation from the packet side, we found that there, in the negotiate, the MS is the 1380 is that changed by maybe some firewall, Cisco firewall to change the MSS.
Oh, middleware helped. Great.
Maybe you can suggest some middleware to
I know what to
change.
suggest about middleware, and it's not complimentary to them.
Okay, thank you.
Okay, thank you very much.
Our next presentation is on DNS over TCP as seen from authoritative servers by Jan of NS1.
So hello. This presentation was full of stars, and it's difficult to make a presentation after one star leaves the stage, but I will try to do my best. My name is Jan. I work for NS1, and we are new to this community. We became the members, so this is our first workshop as members, and I'm keen to present my recent research. Just before we start, I would like to just quickly introduce NS1. We are a DNS service provider. We have Anycast network. We also provide our services on dedicated on-premise servers for certain companies. And we have really nice integration with APIs. And I think the killer feature of our platform is something we call filter chain. So for normal DNS records, you can assign some metadata to them, and then when the answer is processed, we actually change the response. For instance, you can remove your servers that are under maintenance from the resource set. You can sort them by geographic distance, and then pick only a few of them and get them to the client. So if you haven't heard of us, please take a look. And this is not how it works. This is how it works. What was my motivation to actually investigate DNS over TCP? So at the moment, we are re-architecturing part of our DNS platform, the part that is responsible for delivery of the DNS to the clients at the edges. And we really we don't really understand what's the behavior of clients when they use TCP, whether it's all in fallback, whether they do it intentionally. So I wanted to take a look at this. And also we like to plan a little bit ahead. So at the moment, DNS over TLS is hot, between stub resolvers and resolvers. Maybe it will be interesting at some point between resolvers and authoritative servers. So we want to be a little bit ahead. And of course, as every DNS provider, we are often like a target of some DNS attacks. So we would like to better understand how we can benefit TCP during these attacks. So this is actually the first experiment I did. I just, or we set up packet capture for TCP traffic on just a subset of our servers. We kept it running for a few days. Then I just tried to look at like how many DNS queries are sent over the established TCP connections. Because if it's only one query, then it's probably just a fallback because UDP didn't work. If it's more queries, then maybe the client is trying to use TCP somehow intentionally. So this is like a histogram. On the x-axis, you will see queries per connection, and on the y-axis, which is logarithmic, by the way, you can see the number of such a connection in my sample. So the peak is somewhere like 1 million connections where a single query was sent through the connection. But there are some connections that were used to send multiple queries. So yeah, when I saw this data, I just signed for this talk, and after that I found out that this is not a good data set. Because when I took a look at the content, I found out that there's a huge peak on the right side. That's our functional test suite. In the middle, that's some misconfigured firewall that's sending complete garbage to the servers. And these small peaks at the beginning of the graph, that's probably some malware. But fortunately, there's a much better data source. There is this day in the life of the internet, which is run by OARC. And I would like to thank you for giving me access to the data. If you're not familiar with this, it basically happens every year and usually one day. And for 48 hours, the organization that take part in this project just collect all DNS traffic on their servers and then upload this as a PCAPs to like OARC servers where it's available for researchers to analyze. I have taken the sample from last year because the results from this year weren't ready at the moment when I started doing this research. Because the sample is really huge, I selected only part of it. I wanted to have their root servers, TLDs, because there's a lot of data from them. I intentionally pick up different servers in different locations with like different amounts of traffic. And I also included traffic, for instance, from AS112. There are pickups from one server run by White. And this AS112 is like a black hole for reverse lookup to private IP addresses that leak into the internet in ARPA zone. I expected that this could be like representative sample. And this sample has 85 million TCP sections, and during these 85 million TCP sessions, only 67 million DNS queries were sent. These were some of my questions that I tried to answer, not always as I expected or only partially. So is TCP used only as a fallback? Do the resolvers reuse the existing TCP sessions? And if they do it effectively, what's their policy on keeping the connections open? If they keep it open for a long time, or if there's some like limited window after which they close the connection, or if it's the server closing the connection. And I was also interested if there is a situation where TCP can actually perform better than UDP for the DNS traffic. So I ran the same experiment as in the beginning. From this subset of data, I just plotted or created a histogram of queries per connection and the number of such connections in the sample. As you can see, there is a lot of open connections that were not used to transfer any DNS query, which was surprising for me. It's 37%, which is quite a lot. I expected a little bit less. 57 or 58% of the traffic is just like opening a single connection. And in the right column, you can see how much is that in the number of queries in total. So 80% of all queries, DNS queries, are for TCP are sent over the TCP session that is used to send only one query, not more. And as you can see, the numbers drop pretty quickly. If we take a look at like 7 queries per one TCP session, we are already under 1% of all the DNS queries in the sample, which is really low. So who's talking TCP? And by talking, I mean like not using it as fallback, but really intentionally sending more queries to the connection. It's Google. Google Public DNS in 99.6%. And then, again, as you can see, the numbers drop pretty quickly. So there seems to be, I'm not really surprised by this because I talked to a few people, and they always told me that the only client that probably reuses the TCP connection they see in their sample is Google. So I just got this confirmed by taking a look at this. Google Public DNS. I have seen a lot of like probably custom tools that like mass check if the domains are available. So they send a single TCP packet that contains, I don't know, 30 queries, DNS queries for names that are pretty similar. I guess that there will be some like legitimate clients. For instance, if you use DIC CLI, you can use keep open to reuse the connection to send multiple queries. And of course, there is a lot of noise in the data, like clients retransmitting the queries several times. Or I have seen a client that sends a query, the server gets the response, and the client like sends the response as a query to the server back. So I tried to remove a lot of this noise from the data sample, but it was a little bit complicated. Can TCP perform better than UDP? That's a question. I don't have a satisfying answer for that. Definitely UDP is a natural choice because it's stateless, so is DNS. It's definitely cheaper for the clients. If it's cheaper for the servers, that's a question because, for instance, some servers do some expensive processing like DNSSEC signing or DNSSEC online signing. And in that case, actually, a retransmit over TCP might be cheaper than like computing the new signature. But there are some things that we don't like on TCP from like from the DNS protocol perspective, and that's a handshake because we want to provide a good experience to the client, so we need a lower latency, and a handshake is something that creates a like higher latency, but it can be amortized. If you have a connection already open, like you can have the same round trip time as with UDP. TCP also has a head-of-line blocking, which means that it's a stream protocol, and it has to deliver the data in the same order as were sent. So if there is multiple packets, one gets lost, and the receiving side cannot deliver the rest of the messages to the client, to the application, because it has to wait for the retransmit of the first packet. So that's a problem. On the other hand, TCP source addresses are really unlikely to be spoofed, which is something that the DNS operators will really like. TCP has a congestion control. I don't know how much effect this can have on DNS, but in general, I recommend Jeff's blog post recent on RIPE blog about the new congestion control protocol by Google. It's really interesting. But I will slightly touch the Nagel's algorithm. That is something that might actually improve the throughput of TCP. So Nagel's algorithms is something that solves like a something that's called small packet problem. DNS has small packets, so that means the problem is that the network devices and even network cards are not limited only by the bandwidth, the amount of data you can like push through, but also by the rate of emitting the packets. This is limited as well. So if you are sending a lot of small packets, you will never use the whole bandwidth. And what Nagel's algorithm does is that it buffers the writes into the socket for a while if there are some data in the flight. So you can actually fit more DNS queries into a single packet. And there's some example, it's completely unrealistic, but if you have 20 queries, each 50 bytes of size, and you will try to send it over Ethernet and IPv6, then with UDP you will have 20 packets, and the total size of that, of the data that will be transmitted is 2,320 bytes. And with TCP, you will have just one message, one packet, and the size will be less than a half. So I was looking into the case or cases, or I was interested in whether this really happens. So this is a next histogram that shows like queries not per connection but per packet. So as you can see, again, 99.8% of all packets carry only one DNS message. But there are there can be found some where you have more messages actually in the packet. And when I was taking a look at the data, if it's less than like 5 queries per packet, it's probably when the Nagel's algorithms took effect and really like merged more messages into the packet. If it's more than 5, then it's likely an intention of the application, and like the more queries were intentionally created. That the huge peak on the right side, that's exactly checking if some domain is available. Yeah, I was also interested whether there's some preference of using TCP, because I expected that this will be. Well, we can probably specialize this to the Google case because it's 99% of the traffic. But I kind of expected that the aggressiveness or the use of TCP or preference of TCP will depend on the query rate. It's not true. It seems to be that there is some trend, but like the mean time between the queries is pretty high. It's usually 10 to 20 seconds. And I also, well, I think there has to be some point where Google decides to use TCP and where it uses TCP only as a fallback protocol, because these are, for instance, 2 e-root servers that I found in the same sample. One is in Atlanta, second one is in New York, and you can see that the server in Atlanta serves more than it's not more than a half, but much more queries than the server in New York. And the server in New York never reuses one, or the clients never reuse the connection for sending more queries, while in Atlanta this happens really aggressively. So there's a lot of open questions. I've learned something, but I don't have answers to everything. I'm really surprised that there are really 28% of connections that are closed without sending a single query. That's quite a lot. I would be also interested in whether there are like network failure conditions that will show a better performance with TCP than UDP. And I don't mean the congestion control. I don't mean the Nagel's algorithm. I really mean the retransmits, where the retransmit will actually help to get a better experience to the clients. I'm also interested what's the retransmit ratio between UDP, TCP, and one of the questions one of my colleagues raised is whether the resolvers somehow group the queries when they're sending it to the server. Like for instance, queries to the similar zone or queries in a relation of type, for instance, MX query followed by A and quad A queries. Yeah, because I didn't have a time to deep more into this, I put all the scripts and tools I wrote on a GitHub. If you wanna like run it on your own data set, or if you wanna validate my research, please take a look. The toolset is rather conservative because the day in the life of the internet data has to stay at DNS OARC servers. So I really didn't want to use some weird dependencies, and all the analysis was done there. So I basically used T-Shark to extract the information I was interested in from the PCAPs and wrote them in basically CSV format, which I then analyzed by Python. So the first step using the T-Shark or Wireshark is the slow part of the analysis. The Python is pretty fast, and yeah, I think I try to like clean the data, so you'll find the scripts there. I try to remove retransmits and invalid packets, server-initiated connections, because there are a lot in the PCAPs, and zone transfers, of course, because these completely skew the results. So that's what I found, and if you have any questions, I will try to answer.
Let's close the question line.
We have about 8 minutes for questions.
So when you see 28% of TCP connections closed without querying, what do you call a connection? A SYN or a complete SYN-ACK handshake?
I think it was complete connection, but now I'm not sure.
Because it would not surprise me in the DNS that you saw an awful lot of SYNs where you answer a SYN-ACK and it just never works because the filtering is the SYN-ACK hitting back.
Yeah.
So you may not have seen that many connections. You may have seen that many connection attempts fail, and you and I would then agree that's what the DNS does.
Yeah. Okay. Yeah. Yeah, that's a good point. Actually, I'm not sure. Maybe I'm really wrong, and it's just incomplete connection. Thank you.
So Shankar Oracle. One really good application space, which I'm going to be looking at in our own organization, is TCP in a proxy situation with something like DNS dist, where you can kind of nail up connections, where that Nagel efficiency that you're talking about should give a lot of benefit. So I know it's a slightly different use case than what you're talking about, but people may want to think about that. The other question I have is, do you know how many, if any, of the authority servers you were talking to provided out-of-order answers?
I haven't checked.
It shouldn't matter with authority.
It shouldn't matter with the authoritative. Yeah, that's my intuition.
But maybe someone like Cloudflare, maybe it does since they're signing. And I don't know.
There's no Cloudflare sample in that data set, so I don't know.
That's true.
Yeah.
Hi, Greg Choules, 3 UK. Regarding reuse of TCP connections, what is the statistical likelihood that the same two actual endpoints are going to want to reuse a connection in the first place? There are millions of sources and millions of destinations, so that it seems to me very unlikely that the same two people are going to want to send the same successive queries.
Well, it's not the same people. It's the client or resolver opening a connection to the server, and then feeding multiple DNS queries to that connection.
But my point is, what is the likelihood that this client actually wants to send a lot of different queries to the same destination? Okay,
yeah, I think I don't know what's the likelihood as a number, but I would say it's pretty high for root servers.
Really? Okay.
Yes.
Okay.
And for CDNs.
Fair enough.
Thank you.
Hello, Daniel from Switch. I was wondering, do you know of any DNS packet capturing tools which are breaking TCP capturing? So maybe your result could be negatively impacted because PCAPs were not fully.
Well, yeah, the PCAPs in a sample are like separated by 5 minutes. So there probably are like TCP connections that were created before this when the PCAP broke, because I have been analyzing them separately. So there probably is some. The numbers are probably not really exact. Because of this, and that's the only like brokenness I'm aware of.
Sarah Dickinson. For those connection attempts with no queries that went over them, assuming that they are full connections, did you look at the longevity of the session?
No.
Because I'm wondering, they could be trying to DOS the TCP service, so that might be something to go back and look at.
It's possible, But I think the case where the connection wasn't really like completely established, that's more likely.
Okay. Well, a last quick question. I'm intrigued. Did you see any evidence that Google are trying to use TCP fast open?
I haven't checked.
So that would be interesting to know as well.
Yeah, that's true.
Hi, Dwayne Russell's from VeriSign. So I also have a comment about the 28%. So I've looked at this also, and I've seen them for a long time. They are real connections with, you know, full establishment and fins and shutdown and everything. There's no query, and I don't think they're long held. I think these are some software out there that's using the root servers as a test of, you know, working internet. And if they can get a TCP connection to a root server, then they say, oh, I'm online, or something like that. It's some kind of connectivity test. I don't think they're really trying to do DNS. I think they're just trying to test their connectivity.
Yeah, this is actually what we observed in our platform. The Thousand Eyes monitoring, they just send a lot of packets and resizing the TCP window, and they use it to measure the latency.
Yeah.
Could be.
Dmitry Kohmenik.ua, I see that you mentioned you think that large number of packets, queries per connection is part of the functional test, and then you mentioned domain availability test. So you mean somebody just trying to check of all the names available for domain registration, or what?
You mean in the functional test?
Right.
No. The functional test, that's something we see in our platform. So we have a various type of configurations, and we have a just test suite that we can run against the platform. So if it runs, it can run over TCP. But if it's UDP, then the client we implemented just opens the session and just sends multiple queries to that existing session. So it's
you mean NS1's own, right?
Yeah.
And you don't have NS1 own data, because I know you have your own DNS platform. Maybe you can compare that to your own platform.
I'm not sure if
you only used DHL data, so you didn't use against your own NS1.
So this is actually from the detail, and the first slide I've shown you. This is from our platform. So it's a different set.
Now it's clear. Okay, thanks. Good luck.
Thank you. Thank you.
Our next talk is about flooding attacks from Santiago of IMT Atlantic.
So hi, and sorry for those who already see the presentation at Drive meeting. My name is Santiago. I work at the IRISA Research Lab and the IMT Atlantic. This work has been done in collaboration with Sandrine Baton and Stefan Borsmeyer from AFNIC. So just to summarize this work, it's about using regular workstations and normal network interfaces to analyze online network traffic at 10 gigabit per second without losing packages. And of course, the idea is to identify sources of DDoS, for example. And you know better than me that there are a lot of DDoS that the DNS face today. There was the Dyn attack, but I consider, for example, the attack that the French server faced on September 2014, where some domain under the Wallis and Futuna ccTLD were used. And the idea is to detect this kind of attacks. So for my current prototypes, I'm designing a kind of analyzer that listens the same traffic than the server, for example, and it will output each seconds for example, the most frequent domains or the most frequent source IP addresses. So the idea is to develop a software-based testbed where I need some different components. For example, a tool that reproduces the attacks, because for analyzing these attacks, I need some data sets, but having access to the data sets is not that easy, and even I need to run them locally at high speed. So the first goal was to develop a generation tool, and then something that will read the packet and analyze them. For future work, I'm interested in classifying the packets before they arrive to the DNS server. We want flexibility. We are focusing on software and commodity hardware because we want to develop flexible tools that could easily evolve in the future, or that could easily take into account other different attacking strategies than those that we know today. So in our lab, we have some workstations. In this case, Carly, Mo, and Larry. They were acquired thanks to the funding from the French National Research Center. And with these workstations, I can reproduce different scenarios where a flooding source attacks a server, and I have my analysis machine that will analyze the incoming traffic. So these are Dell Precision workstations with dual socket with different amount of RAM. They run on Debian, and they have different network interfaces at 10 gigabits per second and 40 gigabits per second. So the problem with relying on software is because the Linux network API is too slow for needs. And this is a challenge that has been identified a long time ago, and some solutions to work around it has been developed. I listed here some of them alphabetically. So now DPDK is well known, but there are others outcome from the academy that are very interesting. However, for our work, we have been focusing on DPDK because it's very stable now, and it has a strong support from the industry and the community. So at least for the first tool, for the generation tool, we choose DPDK. And to show the challenge that we have, we can compare it against a tool called SOAP that it has been designed to reproduce reflection attacks. This tool is written in C. It depends on the Linux network API. And when it runs on one of my machines at 2.2 gigahertz on a single core, it is able to produce like 600 kilo packets per second, fully random request. So at that time, we found a tool very interesting called MoonGen that provides an interface between DPDK and Lua. So it is very easy to create scripts that will control the packet generation, letting all the hard stuff to the hardware. This MoonGen can be found in its GitHub. And on top of MoonGen and DPDK, we have developed Gigalop. And Gigalop is a tool that generates a lot of packets. And if you would like to read a description of this generator, you can take a look to this paper. So what is Gigalop? It's a 300-line script that is able to saturate with using a single core, 10 gigabit interfaces, which means more than 11 million full random packets per second. It takes advantages of different DPDK characteristics as batch processing. So it sends directly to the network interface a batch of packets that are filled with callback functions. And to take a look to the CPU requirements of our script, we can look at this figure that shows the amount of packets per second in tens of millions. In this figure, we compare SOAP, a MoonGen sample script that produces simple and non-random packets, and Gigalop, of course, at different CPU frequencies. And SOP at 2.2 gigahertz, as I already said, it produces like 600 kilo packets per second. The MoonGen example script saturates the interface even at the lowest frequency, and Gigaloop needs 1.8 gigahertz to saturate a single interface. Gigaloop scales as MoonGen. So for example, on a quad-core CPU, reserving one core for control, we can use the other 3 cores to saturate 3 gigabit Ethernet ports, so we can produce more than 30 million packets per second. And to play a little bit, we benchmarked some DNS servers. Since we don't have a 10 gigabit Ethernet switch yet, we used both ports of the network interface to plug a flooding machine using that will run SOAP and Gigaloop, and on the other port we connect a machine that runs DNSPerf. So the server at the time ran Debian Jessie with the kernel 3.16. It serves a 3 million record example.com zone, and we tried Power DNS 3.4 and Bind 9.9. Bind was set up to use a single core. The idea was to run, of course, DNSPerf while we were flooding the server. Gigaloop, as I said, it produced 11 million packets per second, and SOAP 600,000. And I was a little bit disappointed with my generator because SOAP has a stronger impact, even if it was very much more slower. For Power DNS, we have some, even for both servers, SOAP, the attack of SOAP was more successful. And why? Because from 100 million queries set, both processes, both servers, got just as a few amount of packets. Most of the packets that we sent were lost between the interface and the kernel. So I did some homework after right meeting, and I upgrade the DNS server to the current Debian stretch, which is the testing version. And what I found is that with a new kernel, the 4.9, with SOAP, I got nearly drops from SOAP. But from Gigaloop, most of the packets are dropped. And Power DNS behaves better, while Bind with against both generator, it responds to every single query. Sorry. So I did all this to receive the packets and analyze them, and this is the ongoing work that we are doing. So for the moment, we are using DPDK and LiveMoon, which is the library underneath MoonGen. This is not written in stone, so I would like to hear also experiences on DPDK and other software frameworks. For this, we are relying on statistic-based tools because to identify heavy hitters, we need to know that the cardinal space is huge for both IPv4 and IPv6, and the special case of DNS is also interesting because we can have random queries at varying lengths, so the cardinal space is undetermined. So for that, we take into account several data stream tools. For example, Count Sketch by Kormod and Muthukrishnan, which is the core of the current approach. We need to complement it with other algorithms to estimate the most frequent elements, such as the algorithm of Misra and Grice. And currently, we are investigating on the entropy deviation based on some work that was presented on OARC in 2010. So to give you an idea what a code-mean sketch, this is a probabilistic data structure that receives every single element in a set and passes by different hashing functions. It's an epsilon gamma approximation, so at the end we will estimate some results. We don't attempt to have a very accurate, a precise or 100 precise amount of frequencies, but we can control the error. The idea is to analyze the 11 million requests, and currently we're able to lose just a few packages using 4 cores of our workstation. This is one of the algorithms that we are testing. Just for every single packet that we receive, we take from the queries the most interesting part. We pass it by different hashing functions. And when the time limit is done, we estimate the most frequent domains, for example. Can I show the video now, or do you prefer at the end of the presentation? Well, I have a demo, but I won't be able to run it on live, but I will let a video for the end of the questions, maybe. So this is a copy-paste of the results that we get from sending 120 million requests that we got from the other machine. And in this case, we loses like 800 packages from them. And we were able to count the number of packets per domain in all the packets. Sorry. In this work, I think there are some ethical concerns that are important. I hope one day the queries between the clients and the servers will be encrypted, even if that means that my work will be very, very complicated because I won't have access to the payload. In my prototypes, I'm not logging the traffic, and I'm also avoiding to linking the IP sources to the queries. And I would like to ask what else is important in this case. I would like to thank both institutions that have funded my research, the CNRS and the Fondation Carnot, as also DNS OARC, because now I have access to the captures, which is important for the future work. Race, because they have found part of my trouble here, and the Lead Moon and Moongen authors, because they have done my work much easier. Thanks for your attention, and I will be happy to hear your feedback.
Santiago, well, thank you for these wonderful numbers, and also thank you for updating the PowerDNS slide.
Ah, okay.
That made us a lot happier. Yeah, I'm Bert Hubert of PowerDNS, sorry. I love the Lua stuff, and I think it's a wonderful achievement to bring the language of the gaming community to the denial of service generation community. That should be wonderful.
Okay, this is also because the South American chauvinism. I'm from Colombia, and Lua comes from Brazil, so I think it's also
we
nice.
Love Lua. We love Lua.
Okay.
PowerDNS is, and NOT is also sort of slowly transforming into a Lua engine. So it's very good stuff. So with that, I do have a request. When you did your presentation at RIPE, I got all kinds of people sending me photos that said, PowerDNS is horrible, PowerDNS is horrible. Avnik just proved it. And my request really to everyone, if you decide to benchmark software and present it, please also contact the authors before you publish your research. And I know it's an academic thing, I know you do valid research and it's very important, but as an example, Anand Budev of RIPE, he also did a whole set of benchmarks, and he got some confusing numbers, and he reached out to all the various authors to say, well, what did I do wrong? The problem is, as software vendors, we have to optimize for the fact that people benchmark us out of the box. This means that we have to tune our software so that it's optimized for 10 gigabits per second purposes out of the box. Then we get complaints from people on their tiny free-tier VPS servers that say, I just started PowerDNS and it tried to allocate a gigabyte of cache. So we are in an impossible situation that people benchmark software out of the box, and then we have to make sure that it really shines out of the box, and then we make everyone else unhappy. So my real request is your research would be more valuable if you reached out a little bit before, and this in no way diminishes from the quality of the research, because right now part of your research reflects how skilled you are with the various kinds of software. But having said all that, I love the name G Gallop, and I love the Lua stuff, and I'm very grateful that you spend time showing that our software needs improvement, and I can recommend the Git master branch. It's very good. Thank you.
Yeah, sorry. Yeah, I didn't thought about that. Sorry. So, and for me, the most impacting was the loss of packets between the interface and the kernel, and yeah. This is an academic work, and yeah, you should thought about that. So the next time, for the next benchmark, I think I will contact all the involved people.
Thank you so much.
Thanks to you.
Yeah, hi, Ray Bellis, IC. Can you go back to the diagram, please, with the 3 servers on?
That one?
No, the picture with the 3 servers.
Oh, sorry.
Yeah, this one. So on the target server, you said you're using 2 NICs here. Were those NICs on the same card, or were they separate cards?
The same card.
Okay, so you could have a lot of PCI bus contention, that sort of thing, affecting the results as well there then. Be interesting to see how those might vary if you had 2 NICs instead of just the one.
Okay. Yeah, the problem with this, as I said, for me, is not the most important part, because I like to analyze. I can imagine that benchmarking the DNS is very important, but there are a lot of variables that I should take into account, as how the NICs are connected, which version of the kernel, yeah. the module for the NIC, etc. And all these variables change their behavior. What I would like to do is to publish this generator. I will check the French regulation to see if I will be freely make it available to see that someone else is able to benchmark. And yes, okay, but I will try that also.
Yeah, it's an interesting project. It's got multiple prongs here. It's both being able to flood or generate the traffic at that rate, but also being able to measure the traffic at that rate as well is very, very important. And the benchmarking is actually quite dear to my heart, as I'll be talking about later. Yeah, it's very interesting. Thank you.
Thanks.
Thank you. Jeff Schmidt. So very interesting work. Thank you. Kind of in the same vein, a lot of these brute force sorts of tests are actually tests of the underlying infrastructure, the kernel, NetFilter, the hardware, things like that. So I think it's important to publish, whether you had NetFilter enabled, for example. There's a dozen or so Linux kernel parameters that make all the difference in the world when you're talking about, super high volume tests like this. So, giving a sense of the hardware, also different distributions come out of the box, configured differently, a lot of times matter a lot, even more than the performance of the application level software itself. So, thank you.
Thanks. Okay. And yeah, maybe this. Okay. So this was just recorded after the launch. On top of the screen, I have the generator that runs on Carly, and at bottom, I have the proof of concept that runs at Mo. So just let me come back here. No, pauses. So the proof of concept, this script will output 20 seconds after it starts the number of packets per domain. And it will uses 4 cores, as I set up here. And in Curly, Gigalob will produce 120 million queries for these 4 suffixes: example.com, hola.com, super evil domain, and I love pizza. So is it running? Okay. So for that, the generator requires around 10 seconds. And of course, the idea is to con all of these packets. So this time I was not that lucky as in write meeting. I lose some 150 packets, but I think that is not that important. So and that's it. Thank you very much.
The last talk of this session is from Mr. Bert Hubert on hyperlog and DNSSEC.
Preparing the demo a bit. Okay, there we go. Okay, thank you very much. It's always a pleasure to be at OARC. It's what I imagine that the living room of DNS looks like. Everyone is there, and it's tremendous, and it's an honor to be here. So, what I'm going to talk about, DNSSEC, I will briefly highlight existing DNSSEC penetration measures, introduce in a very lightweight fashion the hyperlog algorithm, spend some time on a party trick where you can estimate the size of a DNSSEC zone by eye. You need to go to those kinds of parties for that to be impressive, though. Then I explain how we can measure DNSSEC penetration using it, and then we have a live demo. And what does it mean? We end up with that, because the results of the live DNSSEC measurement demo are not pretty. Very briefly, who am I? Why do I tell this stuff? We keep running into people that last tried PowerDNS in 1999 and said, wasn't that PHP MySQL name server? And that may have been true at one day, but these days, yeah, we're quite old. We power a lot of domains. Around 30% and 50% of all domain names we can measure. The 50% part is more in Europe. The 30% part is the rest of the world. The recursor, there are lots of super high quality recursors, so we are tremendously lucky that we can pick so many great things like bind and unbound and not, and PowerDNS recursor. The things we do a little bit special is we have RPZ, and we've been doing the Lua thing since 2005, I think. So. And finally, we have the new kid on the block, DNSDist, our big load balancer and denial of service filter, which I think might be the subject of a lightning talk. Is that correct? Who knows? Who knows? So, DNSSEC, existing measurements. Lots of people present numbers. These are gathered, and these numbers are, of course, official. Some of these numbers are surprisingly hard to get to. So you have to scrape them off a bit of JSON or grab them from a website. But you can find how many DNSSEC delegations are there for various zones. These have been aggregated. There is a graph, a live graph of the Dutch penetration made by PowerDNS contributor Kees Monshauer. Frederik Cambus has a list of officially published numbers, and Rick Lamp has a huge list of DNS statistics. And I can only imagine how much work gets into that in finding all these numbers. It's a lot of work, but there is also bias. The registries that are proud of their DNSSEC achievements are probably also proud to publish their numbers. The ones that have 25 DNSSEC delegations may not be as likely to publish those numbers. So with the very precise official measurements, there is a role for less precise measurements that measure the entire internet. And that's what our demo at the end of the presentation will do, if it works. Can we do statistical measurements of DNS? Can we find out from the outside, without having access to zone data, how many secure DNSSEC delegations are there? And it turns out that through statistical measures we can get quite close. They work especially well for NSEC 3, depending a little bit on how it's configured. They work unexpectedly well for NSEC even though you might not expect to be able to do a lot of statistics on there. And with some work you can even estimate how many delegations there are in the zone even without DNSSEC, but that's the least reliable stuff. The techniques we use are related to, or even very close to, the super impressive hyper-log-log algorithm, more about which later. And the utility of these measurements is that we can measure the DNSSEC penetration for the whole internet in a script that runs in 3 minutes. And we can run that every day. That doesn't mean that those numbers are as good as the officially published numbers, but there are a lot more of them. So who here knows what hyper-log-log is? Okay. Who would consider themselves an expert? You can leave now. Okay. What hyper-log-log is an algorithm for quickly counting how many distinct things are in this list. So say you have 1 terabyte of DNS queries and you want to figure out how many different queries are in my terabyte of DNS queries, because they're not going to be 1 terabyte of unique DNS queries, unless you're under a very special kind of attack. If you have a terabyte of data and you want to count that, that might cost you a terabyte of storage, which is quite slow. Hyper-log-log is a smarter way of doing sort minus u with your big data and seeing how many unique things come out. It's not more than that. It is, however, also not less than that, because it's utterly amazing the way it works. Tomorrow, Alexander Meyerhofer gives a presentation which goes into deeper depth about hyper-log-log, so I have arranged that I will stick to the hand-waving explanation, and he will do actually better numbers. So what's the core concept? Let's say I have a bowl, and this bowl is full of marbles with little numbers written on them. And those numbers are between 1 and 1 billion. And I have my bowl here, and I take a marble out of my bowl, and I read what is the number that I can read on my marble. And if the numbers range between 1 and 1 billion, I'm likely to get a number that's like 225 million, or maybe 500 million, or maybe 100 million. But if my bowl is like this big, I would be super amazed if I took a random marble out of that bowl and I got number 12. Because between 1 and 1 billion, the chances of me getting such a low number are very tiny. Of course, this is statistically speaking bullshit, because every number is just as likely as any other number to come out. But still, if I had this bowl with numbers between 1 and 1 billion, and I would pick one number and it would be 12, I would be highly suspicious. This is the core concept behind hyper-log-log. That if I start picking numbers from my bowl, and I just find the lowest number that I can get out of my bowl, this tells me how many different numbers there are in the bowl. It's amazing. Conceptually, intuitively, you can wonder, is this true? Is this likely? And 2 tests are, of course, possible. If there are 1 billion marbles in my bowl, be rather tiny marbles, but okay, eventually I will get the marble with number 1 on it. Might take me an afternoon, but I'll get there. If there is only 1 marble in there, the chances of me picking number 1 are 1 in a billion. So intuitively, it makes sense. The lower number I find, the more marbles there will be in the bowl. Now, of course, there is a rather large element of chance in there. I might be lucky. I might suddenly pick number 12 out of the bowl without there being 1 billion marbles in there. So what the actual hyper-log-log algorithm does, it starts picking numbers and sees how far they are away from 10 million, 20 million, 30 million, 40 million. So in that case, 10 million and 12 is just as spectacular as number 12. Jeff, am I getting it wrong?
You're right.
Okay. No, this is so it's still it's utterly magic that it works that way. But the way hyperlog gets more accuracy is that it compares these various. You might say I have 1,000 numbers I'm interested in, and I'm seeing how close the numbers get to that. Works really well. However, we are in the business of counting domain names. We are not in the business of counting numbers. How do we convert a domain name into a number? With a hash, of course. So, of course, we do everything with a hash. And it works really well. So far you might be saying, look, I read about this hyperlog stuff and it sounded utterly magical, and now you're just talking about a ball with marbles in there, and it doesn't sound that magical. Remember that counting a terabyte of numbers would cost you a terabyte of storage. How much storage does hyperlog need? 1.5 kilobytes to achieve a few % accuracy. That's 9 orders of magnitude less. So if you see people raving about hyperlog, realize they just saved themselves 9 order of magnitudes in storage. This could fit on an FPGA. And I'm pretty sure that people do that kind of stuff. So it's incredibly impressive. And the reason it's able to get away with that, it turns out that the algorithm still works. If you don't even store the lowest marble you found, you only store the number of leading zeros. And that's why you can get it down to 1.5 kilobyte. It's tremendous stuff. Now, how does this apply to DNS? DNSSEC, of course, cannot deny the existence of a domain name by itself, because DNS, if you want to deny the existence, we say there's no answer to your question, and we cannot sign the empty answer. We can actually sign the empty answer, but it would be universally useful. So DNSSEC signs these ranges. It says between this hash and that hash, there is nothing. Or between this domain name and that domain name, there is nothing. 95% of you know all this, but I started to worry a little bit that if we do no longer explain the DNSSEC basics, this will be a DNSSEC only conference, because you have to already get DNSSEC to understand any of this. So by all means, do include some DNSSEC stuff in there. Right now, NSEC 3 is hashed. When it was launched, I understood that 3 people really understood how it worked. I stand by that claim, having implemented the stuff. I look forward to NSEC 5 increasing that number by 2. Anyone that says NSEC 3 is easy has not implemented a resolver and a signer, by the way. So, the relation between hyperlog and NSEC 3 is a hash already. So if I want to count the number of marbles in my bowl, I don't have to hash domain names, I can just use the hash. That's on the NSEC 3 record. How do I pick marbles out of the bowl? I just keep asking millions and millions of questions, or it turns out thousands of questions are sufficient. And each time I ask a random question for a name that does not exist, I get 2 NSEC 3 hashes back as an answer. So this is a very easy way to grab marbles out of the bowl. And based on the NSEC 3 hashes, we use the hyperlog trick to look at the distance between the hashes. So this is the party trick. We might be at such a party tonight. There are 2 examples here, one from the .nl zone, which is of course the most, has the absolute highest number of signed delegations in the world. And I sent it a random query, and the answer came back that between these 2 hashes, Q2HNIK and Q2HO, nothing existed. So you can see that we have 4 digits of base 32 overlap in the range. So there are a lot of hashes there, because the hashes are so close together that this one and that one had an overlap of 4 base 32 digits. If we send a query to the Luxembourg zone, which is slightly smaller, we see that the overlap is actually only 2 digits. So from this, by eye, we can say, look, the number of delegations in the Luxembourg zone is somewhere in the order of the square root of the number of delegations in the .nl zone. So for the .nl zone, it's like 2.5 million, and for Lu would be, well, 1,000 something, 2,000 something, in that order. So this is my kind of party. So how do we measure? I admit I went a little bit overboard, because I wanted to see not only can we do these measurements, but can we do them really quickly. So there is an algorithm. The NS1 presentation told you how many queries you get per TCP IP session. Obviously, I did not run this script on that day. So what we do in parallel for a TLD, we gather all the name server names and all the IP addresses associated with them. So that gives us 10, 20 IP addresses for a zone. And we set up in parallel TCP IP connections to all those IPv4 and IPv6 addresses and start sending them random queries until we have 4,096 or 16,348 queries, and we do the statistics on that. I originally did this query over UDP because UDP is fast. Turns out that there are now more than 2,000 or 1,500 TLDs. Many of them have some kind of rate limiting device in front of them. So my bulk UDP measurements, they were not being appreciated. They were also not being answered, and I had to implement fallback to TCP. And I thought, sod it, I'm going to fall back to TCP IP immediately. And this had a very interesting upside, because it turns out no one limits anything on TCP IP. So that's the first thing I noticed. The second thing, I asked my friends at SIDN if they could see my measurements. And they could not see my measurements. Because why can they not see my measurements? The monitoring stuff, DSC, sees only the first question in TCP IP session, then it gives up. So if you have any dead bodies to hide, the second question in TCP IP is where you should be. This actually has uses, and is something to ponder for any monitoring infrastructure that's used for more than eye candy. Because people could hide a lot of stuff in the TCP IP session. I wrote this in a language called C++, which unlike, we hear that Go is getting all the love. The C++ people have also been working on this fine language, and the 2014 variant is worth a look if you want to do somewhat high performance things. So how fast is this? And I could not let go of this, so I kept optimizing it until it measures a complete modern NSEC3 zone in 0.3 seconds. So what does it look like? Oh, this is, okay, I have to cover this first. How does it actually work? NSEC3 has this range that says between this hash and that hash there is nothing. We use the left part as the, remember from the marbles in the balls, where we say we've checked the distance from 0 and from 1 million and 2 million. I use the left-hand side of an NSEC3 as start here. So I just measure the distance between the start and the end of an NSEC3 hash. We make a lot of measurements on that. I cheat. I only use the first 64 bits of the hash. There's a small amount of inaccuracy there, but it's a lot easier to do the numbers that way. And we average the fraction of the whole NSEC3 space that is covered by these ranges, which is the same thing as finding the lowest number that you find in the bowl of marbles. But this is what it looks like. This is where I measure .nl, one of my favorite zones. The default number of queries is 4,096. We send that to all these IP addresses, and after 0.26 seconds, it reports that there are 2.5 million delegations in the .nl zone, and it outputs that helpfully as a bit of JSON. How accurate is this measurement? This was done this morning, so I come to 2.5 million based on 4,096 queries. And the actual number this morning is 2.6 million. So it's 4% in that case. Does it get better if you do more measurements? Yes. If you double the amount of queries you do, you get closer and closer and closer to the real number. The interesting thing is you see that we approach, not entirely, but we approach the number from below. An actual real random measurement would dance around. So there is probably some undercounting effect, because and this might, for example, be there are these wrapping NSEC3 ranges. Maybe one of them was confusing me. I don't know, but in any case, this is quite close on how you can get. And if you are willing to spend 65,000 packets on it, and we just saw, I think, 2 billion packets pass by during the previous demo, so I think we can do 65,000. Of course, it doesn't have to be a power of 2, but being the geek I am, I do that kind of stuff. At this point, I'm going to start the actual scan of the internet. So what does that look like? Can anyone read this screen? Yeah? Okay. So this is the whole algorithm. So first we retrieve the root zone, which is now a stunning 2.5 megabytes, by the way. Then we extract from that all the delegations, and we add co.uk and com.br. Of course, we should be adding all kinds of other second-level TLDs, but we're not. And we are removing Naru. Why are we removing Naru? I don't know. Naru has either implemented a very clever TCP IP-based load balancer, or its database backend is utterly slow. It sends back one answer a second, which is fine for production purposes, but not if you want to do a 3-minute demo during your presentation. This also uses the wonderful big data infrastructure called Parallel. And if you ever think that you need a whole big scheduling algorithm to launch 25 containers and whatever, you can also pipe your command through Parallel. And it's a very nice way to get your stuff to run in parallel. So let us run this stuff while I proceed with the rest of the presentation. Boom, here we go. So let's see if it is working. Yeah, it's generating 6.7 megabits, 20 megabits of stuff. So let us keep this running as I move on with the presentation. There are still zones out there that have actual authoritative data in them. And like .de, and they mess with our measurements because this in-zone data gets signed. There are whole MX records. You can host your whole business in the .de zone, which is rather a nice service as historical roots. So we need to measure against that because in this way the .de zone looks surprisingly successful on the DNSSEC front. So what the software does is whenever it sees an NSEC range, it counts if there was a DS type in the set. And then afterward it checks which fraction of NSEC 3 ranges had a DS in there and calculates the amount of actual secure delegations from there. The .top zone is opt-in, or at least everything in there has an NSEC 3 record. So in the first run of my software, .top looked like the most successful DNSSEC domain in the world. It turns out they have 2 signed records. So this is how we measure .de, and different in this, does this laser? I don't know. Oh no, the laser doesn't show on the screen, of course. Here you see that in bold there's a thing called secure factor where we measure which percentage of NSEC 3s actually had a DS set, and that's like 16%, which gives the secure delegation estimate for Germany of 71,000. Top, it does the same kind of, so it starts with 3.6 million secure delegations, and then it turns out it goes down all the way to 12 if you run the math really well. NSEC. There are still NSEC zones around. Wouldn't it be wonderful if we could do this trick on NSEC as well? The problem is an NSEC record is not hashed. Or the goal of an NSEC record is not to be hashed. So it's just words, letters. But we can still say, cannot we treat the name of the NSEC as a number? And then find the difference between the start of the NSEC record and the end of the NSEC record. And it turns out if you do this really well and only use the host name characters like A, Z, 0, 9, and dash, then you can map all names to a 64-bit number space, which is of course entirely not randomly distributed. Because there are a lot of areas where there are no words, like if you start with X, Y, Z and stuff, there's nothing going to be there. But I know from long experience that there are a huge number of domains that start with the word power. So originally you would think you could not do this trick on a sort of NSEC 3 pseudo 64-bit range, but there's a thing and, where you can say, Bert, this cannot possibly work. Stop doing this stuff. But there's a thing in statistics called the central limit theorem, which means that if you average enough stuff that is not normally distributed, it will end up being normally distributed. But you have to measure a ton of stuff. So does this actually work? This is the Swedish domain, 16,384 measurements. We do all the numbers, we crunch them, we compare them, and it comes up and it says 600,000 secure delegations. What is the actual number? 700,000. So this trick does not work as well as the NSEC3 hashed one, but it's better than nothing. Of course, the Swedish people publish the actual number, so we don't need to do this trick. But the trick still works. Few words on precision. NSEC3 appears that you can get it as precise as you want. The NSEC one is very vulnerable for gaps. So let's say someone has a domain PowerDNS 12345 and PowerDNS 12346. That briefly generates the impression of 37 to the power of 12 domains, which is, no, it's unlikely. So this one is very vulnerable to outliers and stuff. So when you run this measurement on NSEC zones, do some reality checks. Another important note is that we measure actual secured delegations, whereas a registry may be counting things for which it had seen a key. Doesn't necessarily mean that the DS is in the zone already, so there will always be little discrepancies. So by now, if we are lucky, the demo has finished and we have just measured the whole internet. And let's see what came out. And indeed, we see only 27 kilobits, so either it crashed or it's done. It's likely done. So yeah, it's done. And what came out is a file called zones.js, which we have moved to the right location, which means that it should now be in a browser. That's the one thing I did not check. Do we have a, yeah, we have a browser. No. Yeah, we have new numbers. So what we see here is that .nl, again, as always, ended up on top. That's because we are cheap bastards in the Netherlands, and SIDN gave a small discount if you sign. So everyone signed. You can sort this in many ways. But you can see here that .nl 2.5 million, com.br 700,000. Why is this table now so very interesting? It starts off, there are only 7 million signed delegations in the world. Let us be super careful and say it's not going to be more than 8 million. 8 million out of the hundreds and hundreds of millions domain names that exist. The other thing that's slightly worrying is that if you scroll down, we have, of course, known success stories. We can see that the Swedish measurement has now significantly changed. That's because it only did 4,096 queries, and the NSEC ones need more. And, but quite quickly, when we scroll down, we're under the 10,000 mark. So there is a very limited number of zones that have more than 10,000 signed delegations. And there's a ton of them that have a few hundred of them. Now, why do I care about all that stuff? These numbers are not that good. And in fact, some of the somewhat successful TLDs only come from successful countries that radiate out. So many of the .nl registrars sign everything they sign, also in .net. So it turns out that if you look in .net and .be, you see a disproportionate fraction of Dutch domains. And we see almost nothing coming from the US itself. So DNSSEC is not a super duper success, and we still need to keep good track of its progress. Because the first thing people do when they have a DNSSEC problem is turn it off. If your domain is in .org, is anyone from Affilias here? Do you feel bad? Okay, thank you very much. That's appreciated. It used to be my advice, don't worry, just do DNSSEC. If there's a problem, you can always turn it off. That turned out not to be the best advice in the world. But from my perspective, given how many signed zones we support with our software, it's sort of an informed perspective. DNSSEC is still on life support. And we need to monitor whenever there is a drop in delegations, because probably there's some reason behind it and people might need some encouragement to turn it back on again, or we at least need to know why they turned it off. If you find the presentation, it has more links and more detail. And with that, I'd like to end this presentation. Thank you.
Hi, this is Andre. For the NSEC problem, why you just don't hash it? Because hyperlocal needs uniform distribution, right?
You could, so what you could do, you could indeed just hash it, but that means I cannot use the left and the right part of the NSEC record because they hash to completely different values. But you might be right. You might be right if you can just hash the name and just stick to that.
Yeah, just generate NSEC-free records from the NSEC you get, and that should solve the uniform distribution problem. But I'm not a cryptographer, I'm more a plumber.
No one is. But you're right, I think, so my disappointing answer is, I think I thought this through a lot and found out that it didn't work, but I no longer remember why. But when I remember it, I'll tweet it, because I'm sure it will be 3 minutes after this talk. Thank you.
Paul Hoffman, so does... sort of two related questions. One is, what happens if a zone is using NSEC3 white lies? And the related question is, are you showing that no one is using NSEC3 white lies?
So the first question is, this does not work. This specific one doesn't work.
That's what I would imagine.
And the second one, my code would utterly explode if someone did that.
And you haven't seen that?
No, it would actually, I have not seen that.
Okay, so this is also tells us something about the deployment of NSEC3 white lies, which is it isn't.
Not in a TLD place.
Right, okay, great.
So by the way, the full source code of this tool is on GitHub, and you can find it. So that's a lot better than believing my recollection.
Right, okay, great, thank you.
Rubik's Cube, Nick.pr. Just one comment on the .pr measurements.
Yeah.
You only measured .com.pr, and we have other second levels with registrations, and lots of them are DNSSEC signed.
Okay.
So that's why there is a discrepancy between our publisher numbers, which is almost 1 million DNSSEC signed zones. So one suggestion would be to take out from Mozilla list or something TLDs that delegate on the third level and then test against those. But the other is actually a question, because when I usually try walking some NSEC zones, not NSEC3, some of them have shown some tendency to break the walk, mostly the ones from Newstar. So I wonder if you've also seen that and if that interfered in your NSEC measurements as well, such as .bs or...
Yeah, so let me see. The NSEC measurements are a lot more fragile than the NSEC3 ones. But I'll answer your questions in order. First, I am not sure if I personally want to host this as a daily running service, because I already have a job. But maybe someone else would be wanting to run this as we continue to maintain the software, and then it would be great to have this Mozilla list. The NSEC one, I have found that there are 1 or 2 zones that I cannot reliably count this way, but I don't know if that was the .biz related one. But NSEC3 is almost perfect. That's the thing I do know.
Okay, thank you.
Thank you.
Hey, nice presentation,
Thank you.
Jan, NS1. Yeah, I have one comment to the NSEC thing. I think that by hashing the names after like you did this, the distribution will be different. I think it won't work. But I'm more interested in you said that you're using only 64 bits from that NSEC hash. I guess it's because we don't have 128 byte integers in C. Have you tried even with like a smaller portion with the number, and how does it affect the precision?
So if we assume that SHA-1 is still strong, at least for this purpose, then I know that if I use 64 bits, I will incur a sort of lack of precision in the order of 2 to the minus 64, which should be doable. And I think in this, we should also be able to do 32 bits, just fine.
With a similar result?
Yeah, but it would not, and since this has a 1% resolution anyhow, we can afford to lose 2 to the minus 32 precision somehow.
Okay.
Yeah.
Okay, thank you.
Jerry, DNS OARC. So DSC has TCP pipelining support. So if that's not working for SID, I don't know what they do.
Maybe they run a very old version. Yeah. I don't know.
No, it's been in for years.
Then we may have a bug, because they could not see my testing. That is one thing that has been confirmed. They looked and they didn't see it. But it could be in many places. So I'm sorry for blaming DSC, because it might have been in the gathering phase.
Yeah, I remember fixing that bug, actually.
Very good.
Hi, Bert. Dwayne Wessels from VeriSign. Did I maybe misunderstood at the start, but I thought you said you could also use this to estimate the size of the zone, or is it only good for DNSSEC?
No, you can actually use this to estimate sort of the density of the zone, which is a little bit trickier to do, because you can, and it can only work for NSEC. Because you have to have all the names in there.
Okay. So if we didn't have DNSSEC, you couldn't use this technique, this hyperlog technique to say...
Because then I never get an answer, then I never get a useful information when I ask for a random domain name. Whereas now, if I ask a random domain name that doesn't exist...
What if you ask for domains that might exist?
That vastly exceeds my statistical expertise, I'm afraid.
All right, thanks.
Okay, thank you very much.
Okay, we're now going to take a break until 4:30 p.m.
When I want Chrome, will I just be able to alt tab to it?
Yes.
Should I start? Well, once you've done what you're done, I'll maybe start it already and
Sure. This is just gonna take like 30 seconds. So are we going to do a quick brief?
Sorry?
Are we going to do the...
No, I've already done it.
For the presenter? Yeah, okay. Did you ask if any of them are going to run the... Because we have a PowerPoint and we're going to have LibreOffice open up this presentation.
So we're going to use the PPT rather than the PDF for that one?
Well, if they want, otherwise I might actually delete it because...
Just I'd stick with the PDF.
Well, it depends on the presenter. Can you ask Evan?
Sorry, which presenter is it? Is it
Evan and Peter.
They've both got PPTs, have they?
No, Evan does a PowerPoint. Peter has got an...
Oh, the open desktop.
Yeah.
Okay, right.
Still have 3 minutes, so...
So we're doing 20 minutes of technical questions? Yeah, they're all very standard. I don't expect any different split than normal for this. Like that was super.
10-5 Q&A, 20 minutes.
Unless you want more time for discussion. I don't think so. Yeah. You could decline. You could decline anything.
I'm going to remove these because it's just giving...
confusing everyone.
Yeah, so arrow keys.
Yeah.
If they...
I think most people will know how to use a laptop.
Okay, PDF's fine for everybody.
Okay.
Whoops.
Then let's just remove these.
No, we're just about there. Oh, yeah. I need to catch a quick one. Paul Hoffman.
Okay, PDF.
30 minutes. 30 minutes as well, so total. So, yeah.
Okay.
Okay, if we could all take our seats, we are now time to get started with our last session of today. Welcome back, everyone. So we're going to start off. Andre's going to talk to us about a DNS violations project.
Hi, this is Andre again. And here I thought I'm done for the day, and turns out I'm not. So you have to suffer with me for one more time. If you've seen this presentation somewhere else, like IAPG or RIPE, there's not going to be anything new in there, so just use your laptops as you are doing anyway. The DNS violations project. This is a thing we started because, DNS is complex. If you ever thought that DNS is simple and you understand it, once you start writing the DNS servers, you will discover the DNS is completely something else, and the slides are also complex because they keep turning it themselves. Can we do something about the slides? Like they... Oh, they like change automatically. Thanks. There's a lot of DNS protocol violations out there, and the DNS resolvers just have to cope with that because, frankly, the end user doesn't really care if the website he's visiting is up to par to the last DNS standards. He just wants to see the website or some other protocol, and because there's a boom in the CDNs, there's also a boom in people writing their own DNS solutions that, unfortunately, often just do the minimal thing. While writing Not Resolver, we started doing an internal list of the issues we found and the workarounds we have to apply for the name to resolve. And the idea was that, okay, we have a quite long list, why not share with the community and do something about that so it doesn't have to be that way. So that way the DNS violations project was born. And the purpose of the project is not to shame anybody, but to better understand the common breakages of the DNS protocol that people make, and to make the DNS ecosystem much better, to share the knowledge that is for the alternative DNS implementers to avoid common pitfalls they commonly do, like, oh, you forgot about this piece of the DNS and you should really do that correctly, because that's 10 people before you did the same mistake. Please don't do it again. And therefore the DNS resolver implementers to verify they can handle all the subtle breakages that are not that serious but that happen in the wild. There's nothing sensitive, like no internal information, just the things you see in the public. So we are not really afraid that this could be used to, I don't know, attack somebody. Here's just the list of the common violations. And as you see, there's a recent boom of CDNs doing DNS. And unfortunately, it seems that the CDNs think that the DNS is just some annoyance they have to implement because otherwise their CDNs won't work. But they don't view the DNS as a core protocol for their service. And we really need to talk with the CDN people to convince them that the DNS is important and is to be loved and cared about. I'll see you the concrete, the specific violations later. So there are just random lists, is just some garbage in the end of the packet. It's quite common. Case-sensitive DNS answers, QNAME minimization related breakages, eDNS 0 or eDNS in general related breakages, and then there's just general stuff. Then stuff some related to DNS and other things. So here's a list of current evaluations we've seen. This is the KMP media, which is something with like software for Windows. I don't really know. I view Windows as a bootloader for games. And it looks like what they are doing is they are allocating some static buffer because the packet is always the same, no matter the content in it. So they pick some random number and they create a static buffer and they send it as it is, including the zeros at the end. Easy to cope with, but unnecessarily, the packet is unnecessarily big. It could be smaller. And they also, the other things they do is they have this smart software that they just append the N1, N2, N5, N6, N7 to whatever name it is sent. So if you ask it for whatever random subdomain for NS record, it just generates this. It probably doesn't break anything, but it also doesn't seem right. So another breakage, we call it DVE, domain violations entry, is case-sensitive name servers. This is just one of the violations. The McAfee name servers is something with a database, and they silently break when 0x20 randomization, this means uppercase, lowercase, is used. As you can see, if you uppercase the B in the fourth label, it will just return NX domain instead of no error. And if they were to return serfail or refused or whatever form error, it would be okay, because you would know that something bad happened and you would just use lowercase and ask again. But if they return the NX domain, it means that the name doesn't exist. So you can't, as a resolver implementer, you can't distinguish between these cases, so you don't know that you should ask again. So this is completely broken. But fortunately, at the right meeting, there was a guy who worked for McAfee, and he might have been partially responsible for that, so he might have some context with McAfee. So this might be getting fixed in future, maybe near future, hopefully. A different type of error, which is fortunately the refused. And if you get refused, you know you might want to lowercase and ask again. So again, but if you uppercase the name, it returns refused instead of no error. And this is wrong because DNS is case insensitive. This is malformed packets on eDNS queries. Again, this is not the only case I've seen. Well, just to make sure, the eDNS was standardized 18 years ago. And if you ask with eDNS 0, you will get a malformed packet. It wouldn't matter if the server just ignored the packet and ignored the eDNS and return normal answer, but for some strange reason, it returns malformed packet. And this is one of the violations I think we as a DNS vendors should not support at all. Because if you break so hard, you should break. This is check record communication, CDN. Again, they also provide malformed response where when EDNS is used. But slightly better. At least it was not implemented. For the CDNs, yeah, they the same company fails to provide NS records when you ask for them. For some strange reason, they don't think it's necessary to implement NS, the full zone, just A, quad A. Well, I'm too optimistic, just A, not quad A. Similar. Then there's stuff that breaks QNAME minimization. Yeah, the NS records are just not implemented there. We had to, because we already had a workaround that used like refused NX domain, but not implemented, was not in the list. So we had to actually add a code point that if you get not implemented a return code on NS query when you are using QNAME minimization, just disable the QNAME minimization and ask again. So this check radio communications forced us to have another workaround in the code. And this one, I wanted to write it with David Lawrence there, and I never got to it. But the good thing is that the Akamai NX domain problem should be going slowly away, because I was told that they already deployed the fix, but it breaks some assumptions of their customers, so they had to revert the fix, and they now have a phased deployment talking with the customers. Just correct me if I'm wrong. So the good thing is they know about it, they are trying to fix that, but the customers are resisting.
Short story, life is easier without customers.
Yeah. Then there's some broken signer. The one just, creates a loop. And the other one is a different type of the loop, that it's wildcard pointing to a wildcard. And I really don't know what software did produce those. It's this is my favorite. I get a complaint that the Gitbook CDN, Gitbook is a really cool service that lets you write a book in GitHub and they will just publish it from the Git repository. But their DNS server is not so cool, because at the beginning, when I started talking to them, they return an A response for virtually any query they received. So you ask for MX, you got A. You ask for quad A, you got A. And unfortunately, I was not able to convince them that returning an IPv4 address for IPv6 address is a bad idea. So they are still doing this. They fixed all other RR types, but not quad A. Because maybe you really want some IP address. Even though, and they fixed a bit with, they had a problem with authoritative answer something, so it was breaking the resolution anyway. Yeah, it's sometimes hard to talk to the people. I will try again when I have enough free time, but now it sort of works, so the resolver just ignores what it hasn't asked for, and falls back to IPv4. This is new one. Google name servers return duplicate RRs. So this is, you get, you ask for IPv4 address, you get 3 same IPv4 addresses back. Again, it is against the DNS standard. It doesn't break much, but it's not correct. And again, it makes the packet bigger unnecessarily. So here are the good stuff. Fixed issues. The domain control name servers were filtering TLSA queries, so they dropped the query or the answer. This is fixed, just within a few days. Google DNS just fixed the incorrect response to eDNS version 1 queries. They were missing the question section in the answer, so this is now fixed as well. It was fixed like last or 2 weeks ago. well, one of the many violations the Czech Radio Communication CDN has had in this case was they were setting 80-bit on authoritative answers. So they probably mix up AA with AD, I guess. I don't know, but it's not there anymore. But it didn't make any sense to have 80-bit, and the domain isn't even signed. This is also fixed, maybe related to the presentation earlier today, that they had an invalid unsigned DNSSEC delegation or is an incorrect record, so again, fixed. Then we have other related work. This is an eDNS compliance project by Mark. And yeah, if you know some people on the list he has, please try to convince them that the eDNS is your friend. So how to submit the evaluation? It's, as I say, it's a community effort, and I'm running it like on myself because if anybody from US wants to sue me, they can. I will just not come to US. And we have a format how to submit this, and it gets reviewed by the other people. Even if I submit a violation, then Jerry or Victor will review my submission. So what we can do about it? As a DNS resolver vendors, we should be patient and educate the people. I try to talk to all of those if they communicate bad. And we should coordinate our plan. And maybe it's the time to say, no, we will not do this particular stuff anymore, and just make a plan when to stop and remove the workaround from the code, because it makes the code more complex. One of the ideas from IPG meeting was if there's like violation, just at a small time penalty, so they suffer only a little. And for the DNS community, I'm very happy to see that this room is almost full, like almost. And be inclusive and include and invite more DNS operator people, more CDN people to the DNS OARC community, so they know and understand how DNS is important and how we deeply care about the DNS, and they should as well. And the other thing would be to promote use of the existing solutions. So it's not needed to write your own DNS server every time you think it's a good idea. Maybe you should look, maybe there's something already existing that you can use. How can you help, like you individually? We have the repository at the GitHub. You can, if you find something, please submit a new violation. We have a mailing list. A decent website would be nice, but I'm not going to write a website. You can also, but if somebody from the community want to help and just write a static website generator from the DVs we have, that would be awesome. And well, you can also join the team of reviewers for the submissions. Yeah, if you know some DNS operators that are not in the DNS OARC community, just invite them, because we all know it's great. Also, you can do the education, like write blog posts about the correct behavior of DNS. And that's it. Thank you. And we have like 2 minutes for questions, so 10? Okay, we have 10 minutes for questions. Great.
Hi, Medica Keo. Not a question, but thank you so much for actually doing this work, because for I don't know how many years I've heard Jeff talk about how terrible and crappy the DNS is, you know, rather than what it was designed for. And so rather than just pointing out the issues, we're actually now getting a community effort in place to solve the problem. So really, thank you, and I'm going to be promoting this in all my travels.
You're welcome. I'm doing it for myself.
You know, in case you're wondering where the Google thing's coming from, you know, I can just quote you one verse. Just the place for a snark, I have said it twice, that alone should encourage the crew. Just the place for a snark, I have said it thrice. What I tell you 3 times is true. Lewis Carroll, The Hunting of the Snark. That text has lots of quotes if you look at it, it's a treasure trove of DNS stuff. It has all been written way before. Look at it.
Thank you for the poetry.
It's not a question, actually. I just want to elaborate on the Akamai thing just slightly, because what's really interesting is that when the fix rolled out, where we found that it bit people was people not using DNSSEC sign zones who were using wildcards, because wildcards are poorly understood by people in the DNS, and they were expecting essentially deep matching behavior. And then when these empty non-terminals all of a sudden appeared where they hadn't been before, things that had gotten wildcarded now were getting no answers. And so that's the assumption of customers that was broken, and some of their domains kind of relied heavily on that. And so now we're actually rolling out an additional feature that allows them to configure a zone such that they can effectively get that, always have that deep wildcard matching. But it was interesting that, you know, and it had already been in DNSSEC sign zones. The wildcards weren't an issue because when we implemented DNSSEC, those all got the empty non-terminals. It was just the ones that were still unsigned.
Wasn't it a tiny DNS that had this behavior? Rest in peace, tiny DNS.
Completely unrelated to ours, but yeah.
Rubinsky.br. I noticed that most of the entries mention end-user domains or end-user networks. But except for CDNs, most of them are not actually writing their DNS software, like the Jet Bank that has a lot of entries in your system. So we might want to look into what they are using and then explain, oh, this is using that brand of load balancer, that's using that brand of software, and then expanding to that, because otherwise people say, oh, this happens with that domain or that bank, say, oh, that wouldn't affect me. But if they see, oh, this affects like this brand of hardware, they say, oh, that can affect me.
Yeah, definitely. But that would mean that the people who violate this have to talk to us and tell us what they are using, and that hasn't happened so far. And well, I would say that 50% of those are the people who wrote their DNS servers.
Yeah. Okay.
But yeah, I completely agree with you. If you find out what's the black box or project they are using, we should change the DVE to be more generic and name the vendor, not the end zone. Yeah.
Matt Poundset, just sort of to comment on that comment, I guess, it really is astonishing the number of organizations that inexplicably choose to develop their own DNS servers. But yeah, if you're having problems figuring out what this is, what those things are, then maybe this is a call for somebody to revive FPDNS.
Do you want to respond to that, Andre?
I'm doing that. I haven't heard anything.
Okay, great. So thank you very much. I think it's very interesting and a great effort. So. Okay, next up we have Ray Billis, and he's going to be talking about ISC's Performance Lab system.
Yes, thank you, Shane. So yes, I'm Ray Billis from ISC. As has been mentioned today, I'm the chair of the program committee. So this is what you get when you don't all submit your submissions by the submission deadline. This is filler, but hopefully not. Okay, so the Performance Lab that I spent some time building last year was a project designed to essentially put performance at the heart of what we do with Bind. We want to be able to test experimental code and also make sure that we're not having long-term regressions in the performance of Bind. So to do this, I've built a system where it's a bit like many continuous integration systems. If you're familiar with the likes of Jenkins, we can have multiple configurations all set up for a rotating sequence of testing. For each configuration, we can specify which Git branch or tag that we're wanting to actually test. We can set configure options on a per configuration option. We can set specific named options if those are what we're wanting to test. And we can set alternate named command line options as well. And there are various other configuration tuning knobs that we can put into there. We have multiple authoritative zones that we have tested in this. There are preset zone configurations. So we have the root zone, obviously, because that's quite important for our custom base. We have an example where we have 1 million delegations in one large zone, so replicating the sort of environment that a small TLD would be operating. We also have one where we have a million small zones all within one instance, so such as you might get from a large web hoster. And we also have a very large zone with 1 million quad A records in it. I'm not sure who would run that sort of zone, but that's what we have. And then we have compatible DNS perf query sets to match each of those zone configurations. And we also have a certain amount of recursive testing support in the system as well. The system is a web-based system, so HTML5 Web UI normally runs under Chrome, should run quite happily under the likes of Firefox. There's a minor bug in Safari relating to WebSockets if you're using authentication. As previously mentioned, it goes through all the configurations that we have round robin, so it will do a whole sequence of configure, build, run, test, and then go on to the next one. If you really need to, you can bump up the priority of a particular configuration temporarily, just to, if you don't want to wait. System produces graphs of its output. You can also export to CSV. There's some experimental code in there for doing A/B comparisons across runs. So you can look at the statistics from one set of runs and then select another set of statistics from another set of runs, then do a t-test on those and see how they compare. The system uses an agent model where we have a quite small piece of code that actually encapsulates the behavior of the bind server and how to actually build it and configure it. And with fairly small changes to that code, you can configure it to build other systems. And I have, in fact, already got support in there for building NSD4 and not 2. There is also a DNS echo server, which is essentially a server that does nothing but reply back with the packet it received, which we use to get a baseline figure for the performance of the hardware. Some of the underlying technology that has been used to build the system is MongoDB, which I know it has its detractors, but it's very handy for the sort of JSON object storage that the system uses. With it being a RESTful and AJAX-based system, JSON being passed around everywhere. So MongoDB happens to be a very, very good fit for that. The middleware that actually handles all the serving is written in Node.js. I did a lot of work in my previous employer building JavaScript-based systems, which some of you may have heard of. Yeah, decided to use that technology there. It's one I'm actually most familiar with. If you're a JavaScript geek at all, making extensive use of JavaScript promises and also the Express framework for the embedded web server that's built into the system. HTML5 web UI with the Twitter Bootstrap front end for presentations, AngularJS for the document model, and WebSockets for live updates. Now, I'll do this isn't yet signed in, so give me 1 second, please. I need to get back in. Glasses off. Just to give you a flavour of what it actually looks like in real life. Okay, so this is the system actually running live. Hopefully, we're on wide network here, aren't we? Yes. If I scroll through, you can see there's a list of the configurations that are currently configured. The two there with the activity bars are the ones that are actually currently running. Although I haven't mentioned it yet, there is actually a little bit of DHC support, so you can have multiple agents running at the same time. Typically, each configuration will have a human-readable label that tells us what that configuration is, just so we can find the ones that we want when we go through it. Each one has a drop-down to select how it's queued, so we can turn one off, we can set it to just run once, or we can set it to run forever. And there's also the priority bump up there, which just applies to the next run, and it then falls back to normal priority. There are then, for each configuration, there are tabulated results showing the last set of runs. So in this case, 600,000 queries per second on a recursive server. And we also then have time series graphs of these. come up shortly. In fact, you can see here a recent change we made, which has had quite a good bump up on our performance. You can zoom in and out of these graphs. Go back to that as well. The graphs can be, if I click on a particular point on the graph, sorry, trying to do this with my glasses on. Let's try that again. Sorry, I'm struggling with this small screen. Let's do it from here. We can actually drill down into the detail of an individual test. I'll explain the methodology a little bit more a little bit later, so don't worry too much about these figures just now. But this gives the individual DNS perf runs. We can even go down to the individual DNS perf run and see the individual results that we obtained during that run, including the sort of per second query rates and all the DNX domain and no error rates, all the standard DNS perf outputs. While the system's running, that's why. It also produces logs of what it's doing, and these are all updated in real time. Sorry, pop at them. I'm not used to using it on a low-res screen like this. So this is now actually in real time updating it with the progress of what's happening in the back end. This is all coming up through the WebSockets interface. And in many cases where changes are being made in real time, for example, you might change a configuration, the name of configuration, and everybody else is logged into the system at the same time. It all comes up via WebSockets and gives them a live update of what's happening on the system. Let's go back to that. All right, I think that should probably do for the, just get the quick feel for what it actually looks like. Let's get back to the presentation. Let's wait 1 second. So the logical architecture of the system, the two parts that are written in Node are the test agent and the REST API server. So the test agent is what actually takes care of doing all of the configure and build steps, and that runs on the same box as the DNS server that's under test. It also initiates the DNS perf software that's going to actually run the test against the client. The REST API server is an embedded HTTP server and also a WebSocket server. That talks to the Mongo database talks to the test client, and anytime there are updates to the Mongo database, those also get pushed back through the REST API server back to the web client. It's a similar technique to that used by the Meteor.js JavaScript framework. The physical architecture we have is 3 servers within the actual test network. Just so we've got access from outside of the building, we have an Apache reverse proxy, which handles our Kerberized logins into the network and also Kerberizes the WebSocket stuff. The one issue I have with Safari is that for some reason Safari doesn't actually pass on the credentials you've used for the main page onto the same WebSocket, even though it's on the same domain name. The bug filed with Apple for that, because it's definitely not right. So we have a 10 gig network between the traffic generator and the server under test, and then a separate management LAN through which all the coordination is done between the systems. The back-end box that's shown here is the one in which the REST API server is running and the MongoDB is running, and the test agent is also running on the server under test box. So the test methodology is that we do all of these standard steps that you'd actually do if you were building, bind, whatever, manually. So it's git checkout, configure, make, and then actually make install, and then actually running the daemon up. Monitor the output from the daemon to make sure it's actually got to the point where it started. Then having done that, we initiate 30 runs of DNS perf, and each of those are run for 30 seconds at a time. And we collect the final QPS figure that's come out of that. To avoid buffer cache issues and that sort of thing, we actually discard the result from the first test. So that makes sure we've basically got a hot system ready and running. And that's also handy for the recursive test, because what we do with the recursive test, again, we just let it run for the first 30 seconds, fill the cache, and then all the remaining queries are done from a hot cache. So that figure you've seen earlier of 650,000 queries a second was for a full hot cache with no upstream recursion. The recursive setup is a little more complicated because we actually need a 4th box that acts as the authoritative host that the recursive server talks to that wasn't shown in the previous diagram. So, unfortunately, benchmarking is very, very difficult. Running DNS perf 30 times, you'd hope that you've got relatively consistent figures, but that doesn't turn out to be the case. And even more bizarrely, when we run bind for, say, so we're running bind for 15 minutes, and we get a certain set of DNS perf results. And actually within that one set, the DNS perf figures are relatively consistent. And then we stop bind, and start it all up again, go through the whole process, and we do a new set of tests, and again the results for that one are very consistent. But they're often not consistent with the previous runs. So the means shift wildly across runs, even though within a run they're fairly standard. And this is somewhat mystifying, and something I'd be very grateful to take feedback from people. Maybe not during the questions, but unless you've got any brilliant ideas. But just as a demonstration of this, this isn't actually a graph from the system itself. Just one produced with a slightly prettier graph package. But this is demonstrating here, the candle bars are showing the mean being the bar in the middle of the candle. The size of the candle is plus or minus 1 standard deviation, and then it's the minimum and the maximum values. So I think perfectly demonstrates what I was just saying. This first run here, more or less 625,000 queries per second, plus or minus 1,000 or so, and that's a whole 15-minute run, and yet the run 3 runs later is up at 640,000 plus or minus 1,000, and why it's not 625,000 run after run after run is quite odd. Now, I have done a lot of work on this to try to actually mitigate this. Essentially, I've been trying to tune the systems that we get stability across the systems at all, and this applies to both the client system and the system under test. Hyperthreading certainly proved to be quite bad for variability. The CPU clock rates, of course, on these modern CPUs are too damn clever for their own good. They might be normally 2.5 gigahertz, but they can turbo boost up to higher frequencies. And despite what some of the manuals say, you try to lock them to a particular frequency and it doesn't work the way you think it did, and so you have to throw away 3 months worth of data and then try again, having found a different way to lock the CPU, and all down to ACPI settings in the BIOS and boot settings and that sort of thing. So speed set plays havoc, turbo mode plays havoc. It's also quite important to try to make sure that, particularly if you've got multi-queue network interface cards, that the individual queues are locked to a particular CPU core with the proc interrupts, for example, if you're using Linux. There's flow hashing on some of the network interrupt cards. So, for example, I even have the DNS perf setting set to always start from a particular UDP port number, so that the flow hashing in theory should be consistent across tests. And yet, even with that, I still get the amount of variability that I've been seeing, which unfortunately makes the students' t-test stuff that I've implemented rather moot, because we're trying to look for 1 or 2% variabilities potentially when we make a performance improvement, because every marginal gain is worth having, and yet we're getting maybe a 5% variability that is currently inexplicable, even though it's the exact same software and something has changed somewhere, possibly Linux scheduler, who knows, but still looking at it. We get some even more strange variabilities. This is the Echo server I previously mentioned, just locked onto CPU 0 and 1. And we have 2 distinct populations of results here. This is one DNS perf instance hitting this, and but got a clear flip-flop. I mean, notwithstanding the fact that we have the variability across those lines. I mean, see the top line there, varying somewhere between sort of 765 and 790 kiloqueries per second. But we have 2 distinct populations, and that itself is still also a complete mystery. So benchmarking is hard. So we're doing what we can to reduce this, but there's still some way to go there. So anyway, that's it. We have through this managed to find some particular issues. We found that delegation zones, in particular the root zone, were very, very much a problem for us. Compression is actually very expensive computationally. Excuse me. Typically, Bind seems to spend about 15% of its time compressing answers. I think if we did DNS2 now, we'd get rid of compression. It's too much pain. There was an owner case preservation introduced in, I think, at 9.11.0, but actually it's turned out to be suboptimal, so that should be fixed in 9.11.2. As I mentioned earlier in one of the other talks, we are proposing to turn on minimal responses by default in 9.12. But the thing that's really improved the delegation performance is this new glue cache, which replaces the A cache, which has been around for actually a while, although it's not widely known. But the glue cache, I think, as I understand it, takes the entire additional section and caches that for simple reproduction next time a question comes in. Just got some graphs to demonstrate this. We've got some slightly embarrassing lines on this, but they go back a couple of years here. This is bind back from 2012 up to the current time. The red line being 9.9. Each point is a point release, so that's 990 on the far left-hand side, and recent 9910, I think it must be on the right-hand side. 910. Blue line is 911.0, 911.1, and the dashed line, what we've got coming in, 911.2. Looking at the big dip that you'll have seen there, slightly embarrassing, we had a change made in 995, I think, and at the same time as 9.10.0 was released, because it had been determined that on some systems it was more optimal to set the -U option, which is how many UDP listeners to have, to be half the number of CPUs that you have. In our lab, that's definitely not the case. I don't have any historic record now of on which systems that really was the case, but we have in any case now reverted that. So now the default -U setting is 1 less the number of CPUs you have, unless you've only got 2 to start with or something like that. That was a change that we observed. We spotted that this is not optimal on current architectures and fixed that. Now, the other big thing, really big thing for guys who are doing root operations with bind is the delegation performance. Our root zone performance, we'll admit, was utterly lousy. That same system that's doing 600,000 queries in normal authoritative serving was only managing 60,000 queries or so when serving the root zone. Now, we haven't got quite the way up to 600,000, but we are now up to nearly 400,000 on the root zone. And that's almost entirely down to the root cache and some of the other optimizations that I've already mentioned. That should make a very big difference for some folks. This is also down to the minimal response as well, but that we hope is really going to put bind right up there for a lot of people. So the software, as of a couple of days ago, is now on ISC's GitHub. Should clarify, this is not ISC supported software. Please do not email support ISC with stuff about it, because they don't know what to do about it or do with it. It's an internal project. I wrote it. It's not been QA'd. It's been my little baby. So I will do what I can to support it. And if you guys have got proposed enhancements, please send pull requests. You may even need some hand-holding if you're going to try to install this, but I'm happy to provide that as best I can. Thank you. Any questions?
Hi, this is Andre. I don't have any questions. I just wanted to say thank you for sharing that, because I wanted to get my hands on that for a long time, so thank you.
Yeah, it's taken some while to get it ready for open sourcing.
Hi there, Dominic Marks, Oracle. I wanted to know if there were any particular reasons why you didn't use tools like Jenkins, Ansible, and so on.
Mostly because I wanted to get a lot of the capture stuff there. Jenkins, as I recall, is very much Java-based originally. It didn't really seem to be suitable. I did spend some time looking at that, and it didn't seem to be suitable. I wanted somewhere where I could have complete control and flexibility.
Thanks.
Evan Thompson, Sierra. This is really cool.
Okay.
I've got a quick question. Any thoughts on expanding beyond just query performance? Maybe provisioning performance? Fun segue into what I'm about to talk about.
I think it would probably be, I'm not going to say impossible, but I think it might be difficult to do that. Something we could talk about. I mean, obviously I know it's something quite close to Sierra's heart. Yeah, normally with the right agents it's feasible. Yeah, we could look at it, yeah.
Great, thank you, Ray. Now, just before I let you go, I was looking at your presentation, and there was a very similar presentation at FOSDEM this year about performance in a different context. And I was thinking, oh, I'm going to ask Ray if he tried turning off turbo boost, and if you did this and that, and you did it all. And actually, your result was pretty much the same as his, which is that it's impossible to get a clean, messy result or a clean result in the end. So,
yeah, what was that other system testing?
What's that?
What sort of benchmark was the other presentation really?
This was Python benchmarking.
Okay, so yeah, I don't know whether it's a particular thing in the Linux scheduler, and there's other things can throw you as well. I mean, at one point, because of the security patches, the big kernel issues that came out about 6 months ago, I upgraded the kernel, and it actually halved the performance on the NICs. So there are bug reports into Intel on that. Fortunately, the systems are well firewalled, so I thought, okay, I'll have to live without those patches, unfortunately, for now, and keep performance where it was. But maintaining a stable testbed has been quite a big challenge. And yeah, it took a long time to get to the point where I was satisfied enough with the system that we could say, well, yeah, that's going to be our baseline now going onwards. If you looked at the data we previously had for sort of the last year when the system was up, it was going up and down. As we said, well, yeah, is hyperthreading making a difference? I mean, on that stable configuration now, it did say on the bottom of the graph, but I didn't actually call it out. Systems were, there's a Xeon E5 2600 series or thereabouts. They're sort of 2.5 gigahertz, 12-core Xeons that could hyperthread, but that's turned off. Sorry, where was I going with that? What's causing that variability is just incredibly puzzling. And whether it's in the NIC there or the kernel there somewhere or the scheduler, who knows? And it would be very interesting to see if other folks try and fire this up on different grade hardware, whether they see the same problems. And of course, it doesn't actually need to run under Linux. I mean, what would happen if you set up a FreeBSD testbed running this? Would you get that same variability? Those are all interesting questions, but ones that I'm not currently set up to answer.
I look forward to follow-up work.
Okay.
Anyway, thank you again.
Right. Thank you.
So next up, we do have Evan Thompson from Sura, who was just at the mic. And he's going to be talking about analysis of DNS server software provisioning performance. And this should be interesting because it's looking at a whole other set of measurements. So.
Howdy. My name is Evan Thompson. I work for Sierra. So I'm going to talk really quick about some testing I did about name server provisioning performance. So at Sierra, I work on the development team that looks after dzone Anycast DNS. This is a secondary managed DNS system that has a web portal and a RESTful API that allows our customers to provision their zones onto our Anycast infrastructure. Currently, we have 18 points of presence. They're up there on the pretty picture. And we're running bind in each of those locations. One of my objections for this year is to push out diversification across those locations. So why did I start looking into this? dzone launched in December of 2013. And last year, we saw quite a bit of substantial growth. We hit 200 plus customers. And I was given marching orders to scale the system out comfortably to 1 million zones within the year. So 1 million zones is it's a tall order. And while we built the system with scale in mind, we've gone back through and we put considerable effort into reevaluating to make sure the system will perform at scale. So we started by reevaluating things we wrote in-house. Our provisioning engine, that's the piece that takes the actual information our customers gives us and pushes it out across the Anycast infrastructure. Our stats collection, our API, our portal. Then we got to the part where we started talking and said, okay, what about bind at scale? And the two obvious things that came to us quickly were, one, query performance, and the next was provisioning performance. And when I talk about provisioning performance, I'm referring to how long does it take to add more zones or push out changes to my name servers when I have some number of zones on them. And we were interested in this because our provisioning engine will interface directly with bind to add and update or remove zones. So the longer it takes, the longer our provisioning process will take. So faced with these questions, we did what any good group of software developers would do, and we Googled it. And looking into query performance, there's plenty out there. We found a lot of information that answered a lot of questions we had. This graph is from the Knot website on their benchmarking section. Thanks for that. But we couldn't really find a lot pertaining to provisioning performance. And there were two things I really wanted to know. The first was, given a name server with some number of zones on it, how long is it going to take to add more? And while I'm adding more zones, what impact, if any, is there to query performance? Because it's all well and good if I can add zones, you know, lightning fast, but if I start dropping queries on the floor, my customers get mad. So I started looking at this with bind, and then to have a little fun, extended out to not and NSD. All the versions are listed up on the screens for you. Before we start diving into test results, quick reference to test setup and test philosophy. In the tests, I kind of wanted to reproduce a real-life scenario we have kind of frequently, and that's onboarding a new customer, small to medium-sized customer. They have about 10,000 zones, and they want to add them all at once. I want to know how long that's going to take and what's going to happen to my name servers while I'm doing that. And I wanted to actually replicate how our provisioning engine interacts with the name servers, namely that it processes things in batches. So while adding zones during my tests, I would add them in batches. And when it came to configuring the name servers, I specifically left that configuration pretty naive. This was done on purpose to highlight kind of a lack of available or information or any kind of information on the topic that had kind of any consensus behind it. Another thing is I would be testing query performance or looking at query performance, but that would not be the focus of what I was testing. So the tests of query performance were relatively simple. What I wanted to do was establish some kind of baseline in my test environment for query performance, and then rerun that test while adding my zones to see if there was any kind of observable change. So the test process itself, I would start with some number of zones on a test machine. I did this with 100,000, 500,000, and 1 million. I would then add 10,000 new slave zones in batches, all from slaving from one machine. The batch sizes I used are up on the screen. I would test this both using written configs and using dynamic adds available from the name server software. While doing this, I would capture how long it took to run each add command individually, how long the overall process took, and then I would use DNS perf from a third-party machine to test any observable change in query performance. So, the test hardware. My test machine and the slave machine, or master server, sorry, are Cisco UCSs, 32 gigs of RAM, quad core, doesn't say it there, Red Hat Linux, RHEL 6. The DNS perf machine itself was just a little VM I had, 2 gigs of RAM, single core, again, Red Hat, RHEL 6. When it came to the zones I was using, the names were taken from the unique permutations of 12 words. When it came to content, I was more concerned with, excuse me, with size over actual content. I wanted to replicate the distribution of size in zone files we currently have on our system. So the distribution I chose is up on the screen and reflects roughly what we have in our system today, just scaled out to the various number of zones I used. As I said a couple slides ago, I tested this at 100,000, 500,000, and 1 million zones. Looking through these, I started to see trends that were echoed across the different base numbers. So instead of boring you fine folks, I chose just to go with the interesting one, 1 million, and move forward. So looking at written configs, this is writing zones in batches using the batch size I used, then reloading or reconfiguring the name server to load in those new zones. For bind, this is RNDC add zone. For NSD, this is NSD control. No, sorry, bind RNDC reconfig. Getting ahead of myself, I apologize. For NSD, NSD control, reconfig, and not C, reload for not. So this first graph here looks at the average time it took to run the name server command to prompt the server to reload or reconfig for a single batch of zones as I was adding in batches. What you can see looking at this is there's a pretty standard amount of time each name server takes regardless of how many zones I've added in batch to run the reload or reconfig command. There's quite a bit of distribution in the times themselves, not sitting up there just over 200 seconds, bind about 51 seconds, and NSD about 19. One thing that kind of got me by surprise was the amount of time it took for me to run the not command. But going back through the documentation, I saw the note there saying that for larger configurations, there is a recommendation to use their binary config database. I'm guessing 1 million fits in there, so we'll kind of cover that later. Looking at the time it took to add the 10,000 zones in total, what I measured here was from the first add command I issued from the last, or to the time it took for the last zone to transfer over onto the name servers. We see with the smaller batch sizes, it's definitely taking longer. This is reflection of I'm issuing more commands that take longer to run. And we see a steady decrease as I increase the batch size. To really get a sense of what's going on, we can zoom in, and we see that for NOT and NSD, they both continue to decrease in time as that batch size increases, where bind kind of holds steady in around the 500 second mark after you hit that 1,000 batch size. I highlight that because I want to come back to it when we get to the dynamic zones, or dynamic ads, I apologize. Looking at query performance, or the effect on query performance here, what I did was I took my baseline for query performance in terms of queries per second, and then compared that to what I was able to get while adding my zones. NOT, I was able to get 100% of what I achieved while adding my zones. For NSD, I saw a bit of degradation down in around the 89, 90% mark, 10 to 11% achieved 80 to 90% of my baseline query performance. And for bind, this is where I saw the biggest reduction. I was able to get about 39% while adding zones using the smaller batch sizes, bumped that up to about 50 as the batch size increased. So obviously what you're seeing here, where there is an effect, it's where you're issuing that reconfig command more consistently for smaller batch sizes. Moving on to the dynamic ads. This is looking at for bind, RNDC add zone, NSD control add zones, and for not using their binary configuration database and interacting with it in an open session and committing those changes. Here we see something completely different than what we saw with the dynamic add times, config add times. We see a general increase in time to run the command as the batch size increases. To get a sense of what NSD is doing, we see that same arc, but on a much smaller scale. Bind and NSD are increasing in terms of seconds, where bind and NOT, my apologies, are increasing in terms of seconds, whereas NSD is increasing somewhere in the realm of milliseconds. One thing keep in mind here is in my testing, you'd start to see that NOT, when you're issuing these commands, it's much like you're interacting with the database. You're opening a session, you're issuing a series of commands and committing them. At the end of that commit, you know either everything has gone through and succeeded, or something has failed and it will fall back in a rollback. So you're paying more in terms of time for a stronger guarantee at the end. Whereas using something like NSD add zones, you pipe in all the list of zones you want to add, and it will then take that list, return, and then continue to add those zones in the background. At the end, you don't have a guarantee on the state. Some might have added, some might have been added, some might have failed. So here you're looking at a trade-off in time for a looser guarantee. It's really down to what you were looking for from your name server software in terms of choices to be made. In terms of how long it took to add the 10,000 zones, using dynamic commands, for NOT and NSD, we see that same downward trend as I'm adding more zones in each batch. Bind has that same kind of decrease in time, but again, sees this constant at 500 seconds once I hit the 500 batch mark. Want to highlight this here because when I first ran these tests, I left the configuration for bind with the defaults for concurrent transfers per NS and concurrent transfers in. I think that's 2 per NS and 10 across the system. So I went back and reran the tests with some pretty high number there, about 1,000 apiece, and I saw this same baseline or kind of plateau. In terms of query performance, NOT again achieved 100% of its baseline. NSD sitting around the 89, 90% of the baseline again. Here we see a huge improvement for performance for bind. With the smaller batch sizes, 100 up to 1,000, I was able to get 100% of the baseline query performance with a slight degradation with the larger batch sizes down to about 95%. When I finished this, I had a bit of time left over, not a whole bunch, but just a wee bit. And I remember talking to someone from ISE, and they had mentioned that in bind 9.11, they would include the ability to compile with LMDB to improve dynamic delete and modification times. So I thought there might be something fun here to look at dynamic deletes specifically for the other name server software as well. So what I did, a slightly different test in terms of timing and how much time I had left. Started with 500,000 zones on my test machine, all master zones. Deleted 5,000 of them, again in batches, and looked at much the same as what I looked at before. In terms of delete command timings, the average time it took to run the command, we see the same general trend as before, an increase for all of them. The scale just slightly different for NSD, milliseconds instead of seconds. When looking at the average time taken for delete, this is where things got a little interesting. NOT and NSD both had that same trend as with the dynamic adds, that downward trend as the batch size increased. Bind kind of flipped the script here and showed a little bit of an increase in time as I was deleting in larger batches. Haven't had time to go back and look into root causes for this, but interesting nonetheless. And finally, with the query performance, see much the same for NOT and NSD as what we've seen throughout the entire tests. Not 100% of the baseline, NSD sitting around that 89, 90% mark. And Bind actually was able to get 100% of the baseline when I ran these tests. Sorry. Moving on to a conclusion here. My personal takeaways moving forward is we're looking at dynamic commands to the name servers over written configs. There's a little bit of a speed adjustment we get. There's less custom I/O. I don't have to write different types of config files for different types of name servers. I just have a generic interface that I program against, which is really nice. And where we did see query impact, that query impact was less or about the same as with written configs. In a world where I have to use written configs, I'm leaning towards a larger batch size, as the time it takes to process that's about the same, but the query impact a little less. Next steps, I'm really interested to talk to you folks here. You're probably a whole lot smarter than me and have a lot more experience dealing with this. So if this is something you have dealt with or maybe thought about, there's a microphone here. We're about to open it up, or come talk to me later if you're a little bit shy. In terms of further testing, I would love to rerun these with some kind of tuned configuration. As I stated, I left it relatively naive on purpose. So again, if that's something you know, I'd love to hear about it. I think there's something interesting that could be done in terms of a more in-depth look at master configurations. Given our products, I kind of stayed focused on secondary. And also expanding these tests out to look at other name server software. Started with Bind because that's what we're on. I then branched out with NOT and NSD because I had a little bit of familiarity with them. Then unfortunately ran out of time with my testing before I could look at anything else. And specifically for DZone itself, like I said, we're looking to diversify and plan to have that completed within the year. And that's it. I'd love to hear from you folks, be it questions or comments. If you're shy, don't feel like talking. If something comes to you later, my email's there. I'd love to hear from you. Thanks.
Thanks. It's great to see all this laid out. We did some testing. I was Matt Pounset from Right Side. We did some basically the same testing about 2 years ago for one of our registrars as we were re-implementing the name server infrastructure there. Different scale. We were running 3.7 million zones in the name server instance at the time. So I started with 4 million and tested 4 million, 6 million, 8 million, and 10 million, I think, zones in the name server. And this was a couple of years ago, so I can't remember all the details, but it was pretty similar results. But I came up to specifically talk about deletes.
Yes.
The main bottleneck you're running into there, of course, is rewriting the NZF file in Bind and similar issues in the other name servers. Our solution for that was to actually patch Bind to hash the NZF file into, I think it was about 1,024 different files.
Okay.
Which results in delete performance that's comparable to add performance through our NDC. So
that's cool.
Yeah.
Thank you.
I think I'm pretty 99% sure we contributed that back to ISC, although I'm not sure if it ever made it into core.
Bummer.
Yeah.
My recollection is that the LMDB stuff superseded it.
That seems entirely reasonable. Yeah.
Sorry, could you repeat that? What the answer from ISC was?
Oh, sorry. Ray says that the LMDB changes superseded figuring out how to integrate our patch into the core. Because, we're not ISC developers, so. Anyway, thanks very much for doing that.
Thank you.
Yeah.
Hi, I'm Andre, and I'm shy.
Well, we're all pretty nice.
Thank you very much for this work. And is it available anywhere so we can, well, test it or maybe integrate it in our testing suite? Because yeah, this is really great and that you did the work, and it would be really nice if you can share this with the community.
I can definitely open it up. It needs a bit of cleanup. I kind of threw some stuff together in Python, so it's a little rough around the edges right now, but I could definitely clean it up and get it out there.
If it doesn't contain passwords, it doesn't need cleanup.
Can we get that on a t-shirt?
No, really. This is a common argument that the code, I'm not very happy with that. This can be solved later. But if you open it up sooner than later, and if it doesn't contain any sensitive information, please do that earlier than later, because then you might get sidetracked to some other projects. So if it doesn't contain any sensitive information, just do it now.
Okay.
Please.
All right. Thank you.
All right. Well, thank you very much. Okay, we are on to our last talk for the afternoon, and that is testing DNS resolvers as in the real world. And it's by Peter Spacek. Sorry if I mangled your name.
That's fine.
Thank you for introduction. This presentation is going to be about project we are developing in CZNIC, but before we start, let me make clear that all the tools work with other resolvers as well. So you are more than welcome to use it for your software. We will be happy to discuss and, of course, accept merge requests if there are some. So main focus here is on functional testing, basically making sure that after run to improve the performance on basis of the previous presentation, we don't break anything and the existing deployments will just work. We have quite short time, so I will be on purpose ignoring security, performance, usability, and other characteristics. So what is the problem? Basically, the DNS protocol itself. It has so much state that it's just impossible to test all the possible configurations and states which resolver might arrive to. State explosion is an obvious problem. Then the protocol allows clients to query with all different flavors, which doesn't help at all. And then even if we were able to cover all the standard stuff, we would have many problems with weird implementations which were covered by a previous presentation by Andrei. And even if we had workaround module which would cover all the weird things, still the users will demand that the resolver has to work even though the network itself is not reliable. So a lot of fun. So it's absolutely clear that we have to limit ourselves to some subset. So the obvious approach, which is often done, is to write handwritten test which queries one single name, waits for the answer, and then checks one single answer. But that's not what users do, right? Users typically open a web browser, and if you try to open youtube.com in Firefox, it will generate a bunch of queries, and that's just the home page. So the approach we are trying right now is to use the real web browser, open a real website, let the web browser generate all the DNS queries, and work with this from this. So on the highest level, we are using the Selenium web test framework to drive the actual web browser. Then we are capturing the traffic. Maybe let me show you a picture. We are capturing traffic between the web browser, which means basically the stub resolver, and the recursive side. And this is captured to a single file. And then the recursive resolver is, as usual, going to the internet and sending queries all over the place. And we are capturing those to another file. When the web page is loaded, we terminate all the processes and then work with the pcap files using the tool with working name of the card, which is generating a test from this. So how does the test look like? In general, it has two main parts. One is the set of queries which the stub asks sends to the recursive resolver and the expected answers. And then the second part of the test is all the information on the internet which the recursive resolver requires to prepare the answer for the stub. Of course, the queries sent by the recursive resolver very much depend on its configuration. It depends if the query minimization is on or off, or all the options you can possibly set in the recursive resolver. So it is possible to rerun the recursive resolver with the same set of queries, but different configuration, then combine all the queries sent to the internet and generate tests from those. So let's say we have a test which has two parts. One is list of queries and expected answers from stub, and the other part, which is basically the data on the internet. So how the testing looks like. We have a special testing tool which is called dcart, and it is running the unmodified binary inside a simulated network. So when we prepare a new version of the resolver, we run it under the dcart tool, and the dcart to replace the queries from the stub to the recursive resolver. When the recursive resolver attempts to contact servers on the internet, the dcart tool intercepts the communication and replies the answers we captured previously. So the assumption here is that if the resolver is getting the same answers from the internet, and we know that the resolver is getting the same answers because we are replying them, well, it should always give the very same answer to the stub. So this is to make sure that the new version didn't break existing deployments. Of course, we can tweak the configuration of the recursive resolver under test. So again, we can tweak the query minimization and the other options. The dcart tool is able to run multiple processes inside one simulated network. So it is possible to set up, for example, unbound as recursive resolver, and in the same simulated network, not resolver which is forwarding to the unbound, and verify that if we reply the queries to the not which is forwarding to unbound, nothing breaks, and the client will get the same answer as always. That's it on the highest level. Well, what is ahead of us? First of all the tools and approaches I described are right now in proof of concept stage. It somehow works, but it requires a lot of manual work. It's not very pleasant to work with that. So our first step is to finish it, get it to some state where it can be used automatically. Then we can generate tests for first, let's say, top 1,000, 10,000, 100,000 websites from our favorite list. And then we can get more fancy and try other approaches. I will be very happy to hear from you what can be tested using this approach by simulating the internet basically for the resolver. We can discuss this, of course, over the beer. I know that I'm the last thing standing between you and the next program. So I really encourage you to have a look. The documentation was updated. There are some basics of the dcart tool, but of course, it's better to ask. So we have a mailing list or talk to me in person. Now I think we have time for our questions.
Paul Hoffman from ICANN. So before, maybe 5 years ago, before I was at ICANN, I actually had to do some simulations of web browsers, just looking for delays and also trying to see straining the network. YouTube is actually easy relative to Facebook, which is actually easy relative to almost any newspaper page. Maybe, I don't know if that's true in the Czech Republic, but if you go to the New York Times, LA Times, or whatever,
Definitely.
and the smaller the newspaper, the more crap they have on the page that is not optimized. And so I live in Santa Cruz, and so we have like the Santa Cruz Sentinel. It just takes forever to do. And I mean, so I actually use that in my testing. So if you want to get more maniacal and sort of more typical, it's hard to say typical because sometimes people only live in Facebook. But for people who don't live in Facebook, newspapers are a great example of queries that don't all go even to the same eventual one. Another thing you might want to add in, and I know this is really difficult, but if you can also control the resolver timing, which I know Deckard is good at doing timing, it's really good to test what the second user sees. So you go to the newspaper page and then another user comes in, say 25 seconds later. So the things that had a 30-second TTL might still be there, they might not, etc. That's actually a really interesting one that I found, again, sort of by accident as I was doing this other testing, is that different recursive resolvers will do hammer. Different browsers will do hammer, by the way, so doing the exact same test from Firefox and from Chrome will get radically different results because Chrome seems to actually be better these days, or at least a few years ago, at saying, my God, I'm going to the same NS record a lot. I'm going to do it myself. I'm not even going to go through the operating systems resolver. They have sort of a mini one for some maniacal things. And so you'll actually get differences there as well. So even more to play with. So thank you for doing this, and I definitely look forward to more on this.
Thank you for the feedback. We definitely want to have a very long list of websites. So I guess that the newspapers will make it to the first 100,000 websites on Alexa or something.
They might, but the other thing is a lot of the websites at the top are actually run better than the ones run at the bottom. And so, for example, YouTube, Google tries as hard as they can to have the fewest, new things come up. Facebook isn't as aggressive, and then again, as you go to less professionally run sites, at least that's the way I feel like American newspaper sites are, then it's pretty much all bets are off. So you might even start in the middle instead of at the top to see what you're going to get.
Okay, thank you. We definitely want to make sure that new versions will not upset the users and the support client will not be ringing all the time. So we probably will start from the very top, so to make sure that the Google works. But then we might get to the weirder places in the list.
Great. Well, thank you very much. I think certainly this has been an area that we've long needed more systematic and better testing. So thank you for being brave enough to start this effort.
Thank you. And once again, this works with other resolvers as well. We were testing this with Unbound and PowerDNS Recursor. Others should work as well. So please talk to us. And thank you.
Thank you. All right. Now we'll hand it over to Keith, who's going to let us know what's going on for tonight and tomorrow.
Okay, well, we have finished ahead of schedule, so I'd just like to thank all our speakers today for getting the slides uploaded in advance and running on time, and indeed for their insight and contents. A few quick things before we finish. Sorry. We have 5 lightning talk submissions, so thank you all to the speakers. We'll run all 5 of these at the end of tomorrow. We'll get at least 10 minutes, possibly more if we manage to run things on schedule. PGP signing will take place at 1:30 tomorrow, probably in the Vienna room, but we'll confirm that. So if you want to do that, send your keys to Matt at pgpsign@dnsoarc.net. Survey. Please, since we're ahead of schedule, if everyone could just take a few minutes before they leave the room this evening to go into that one-page survey and give us your rating on the talks, we'd really appreciate that. For the social this evening, you need to get the Metro. There are directions in the email that you received. If you're confused about getting the Metro, then basically we will meet in the lobby at 6:30. You can all wear OARC football scarves so you don't get team scarves so you don't get mistaken for the football fans. and we can go on the metro together. Basically, you can just buy you can buy a ticket for cash, or you can buy 10 tickets and then you can just reuse it for 10 people, just putting it through the gate repeatedly. So really, it's easy. I'd also just like to thank Joao as our man on the ground in Madrid for arranging the social for us, which is a big help. So, so thank you, Joao, for that. Other thank yous today. Thanks to all the volunteers who've helped out with things like timekeeping and the PC session chairs. And of course to our sponsors, ICANN for hosting the meeting and covering pretty much all of our costs, VeriSign as our main sponsor, and also to Salesforce. I think that is basically it. As far as the social is concerned, if you can't make it, please let us know. We're full, but there are a few spaces. And don't forget to wear your badge, and your badge needs to have a pink sticker to get into the social. So basically, that's it for today. Oh, sorry, Matt wants to say something.
Yeah, just a quick note about the PGP signing. I actually don't have any keys from anyone yet. If you do want to participate, I'm going to set a deadline of the first break tomorrow, because there's a bunch of prep work I have to do after getting all the keys before we can start. So yeah, so please get those to me by the beginning of the first break tomorrow. Thanks.
Okay, so fill in the survey and either make your own way to the social venue. We strongly recommend Metro. Everything else will be stuffed up. Or meet in the lobby at 6:30 for escort to that. Okay, thanks. See you tomorrow.